Welcome to another deep dive. Today, we're going to be looking at baby Mandelbrot sets
Yes.
and how they show up in parameter spaces of generalized McMullen maps.
Very cool.
You sent over some really cool research, and I'm excited to dig into this with you.
Yeah, it's a really fascinating area. And, these baby Mandelbrot sets are like these hidden gems within this intricate landscape of complex dynamics.
Well, I like that. I'm ready for a treasure hunt.
All right, let's go.
But before we start digging, let's set the stage a little bit.
Okay.
What exactly are generalized McMullen maps? I know they're a family of complex rational functions,
Right.
but what makes them special?
So, they take the form R sub n, a c of z equals z to the n plus a all over z to the n plus c.
Okay.
And the parameters n, a, and c are really key here.
Okay.
By adjusting these, we can explore a vast space of functions that generalize both quadratic polynomials and the classic McMullen maps.
So we're casting a wider net than just the usual
Exactly.
quadratic polynomials we see with the Mandelbrot set. Speaking of the Mandelbrot set, can you give us a quick recap of its significance?
Sure. So the Mandelbrot set, denoted by M, arises from iterating quadratic polynomials of the form z squared plus c.
Right.
And it's a visual representation of which values of c lead to bounded orbits when we start iterating from the critical point 0.
Right. The bounded or escaping to infinity.
Exactly.
So how do these generalized McMullen maps lead us to these baby Mandelbrot sets?
Well, a baby Mandelbrot set is essentially a homeomorphic copy of the Mandelbrot set that we find embedded in the parameter spaces of other function families.
Okay.
And our goal today is to kind of understand how these mini-M's emerge within the parameter spaces of these generalized McMullen maps.
So it's like finding little Mandelbrot universes
Right, exactly.
within a larger mathematical cosmos.
Yeah,
I like that.
that's a good way to put it.
Now, I know these parameter spaces can be a bit abstract. How do we actually visualize them?
So that's where the images you provided come in. They're generated by assigning colors based on the behavior of the critical orbits for each parameter value.
Okay.
And this creates visually striking patterns and allows us to identify regions of interest.
So we're using color as a visual language to decode the dynamics of these functions.
Exactly.
But how do we even begin to find these baby Mandelbrot sets within these colorful landscapes?
Yeah, so a crucial concept here.
I'm guessing it involves some serious math.
It does. It does.
Okay.
A crucial concept that helps us on this treasure hunt is the notion of polynomial-like maps,
Okay.
introduced by Doody and Hubbard.
Right.
These maps, while not strictly polynomials, behave locally like polynomials.
So we're looking for regions where these generalized McMullen maps simplify and start to resemble those familiar quadratic polynomials.
Exactly.
But how do we pinpoint these regions mathematically?
That's where Theorem 2.3 comes in.
Yep.
It lays out specific criteria that guarantee the presence of a baby Mandelbrot set within a given parameter region. Essentially, we need to construct two special sets, U prime and U, and then show that our generalized McMullen map behaves like a quadratic polynomial within these sets.
So it's like setting up a controlled experiment within this vast laboratory.
That's a good way to think about it, yeah.
Of parameter spaces.
Yeah.
Are we focusing on any particular parameter planes within this vast landscape?
Yes. So the research that you provided focuses on exploring the A-plane.
Okay.
Meaning we've fixed the parameter C and let a vary.
Okay.
More specifically, we're looking at the case where the magnitude of C, written as C, is greater than 1.
Why the focus on C being greater than 1?
That's a great question. Lemma 2.5 provides a clue.
Okay.
It tells us that when phi is greater than 1, there are n solutions to the equation C plus or minus 2 root equals a to the 1 over 2n.
Okay.
This hints at the possibility of finding n baby Mandelbrot sets within these parameter planes.
Interesting. So we're already seeing a potential connection between the parameter n and the number of baby Mandelbrot sets.
Exactly.
Now, I've noticed that Theorem 1 plays a central role in this research.
Yes.
What's the key insight that it reveals?
So Theorem 1 is kind of the climax of our investigation in the A-plane.
Okay.
It states that for C, greater than or equal to 6 and sufficiently large values of n, we can guarantee the existence of n primary baby Mandelbrot sets.
Wow. That's a pretty powerful result.
It is.
It's like we've uncovered a mathematical recipe
Yeah.
for generating baby Mandelbrot sets.
Exactly.
But I imagine proving this theorem requires some intricate steps.
It does.
How do we actually go about establishing the existence of these n baby Mandelbrot sets?
It's a multi-step process. So first we define special regions in the A-plane called WUSUB. J subregions.
Okay.
These regions are carefully constructed to enclose potential baby Mandelbrot sets.
Okay.
And they have really fascinating shapes. Nearly circular inner and outer boundaries, and then ray-like boundaries formed by arcs of parabolas.
So even the shapes of these regions are dictated by equations.
Exactly. It's all very precise.
So these Wu sub J sub J subregions are hunting grounds.
Yes.
Where we expect to find these mini-Ms.
Precisely.
But how do we know for sure that these regions actually contain baby Mandelbrot sets?
The key is in showing that within each Bo sub J sub region, the generalized McMullen map, first sub, actually behaves like a quadratic polynomial on a specific subset of its domain, denoted by U prime sub A k.
So we're zooming in using these Wu sub J sub regions
to
isolate areas where the map simplifies and behaves in a way we understand.
Exactly.
What happens within these special subsets, the U prime sub AK?
So this is where it gets visually intriguing. As the parameter A moves around the boundary of a Wu sub J sub region, the critical value of the map embarks on this fascinating dance. Moving in a way that fulfills the final condition of Theorem 2.3.
I'm picturing a little dot swirling around these intricate boundaries.
You got it.
It's like watching a mathematical ballet unfold. But I'm curious about the specifics of this dance.
Sure.
What does it mean mathematically for the critical value to move in this particular way?
It means that as we trace a path around the boundary of the sub J sub region, the critical value winds once around the corresponding critical point. This winding behavior, referred to as having a winding number of 1, is crucial because it's a hallmark of that quadratic-like behavior we're looking for.
So it's not just about finding regions where the map behaves like a quadratic polynomial.
Right.
It's about having the right kind of twist as we go around the boundary.
Exactly.
And it sounds like this winding number is a key concept in proving Theorem 1.
It is.
And establishing the existence of those n-baby Mandelbrot sets.
It is, yeah.
This is really fascinating. We've explored the concept of generalized McMullen maps. The significance of the parameter C being greater than 1. And the role of these special Wu sub J sub regions.
Yes.
We've even touched upon the dance of the critical value and its connection to the winding number.
Right.
But I'm sure there's still so much more to uncover.
Oh, yeah, definitely.
What other avenues of exploration do we have ahead of us?
So we've only just begun our journey. The research also delves into another intriguing scenario where we set C equal to T times A, creating diagonal lines in the AC parameter space.
So instead of fixing C, we're creating this dynamic relationship between C and A.
Exactly.
I'm already curious to see how that changes things.
Yeah, it leads to some very interesting stuff.
But before we dive into that,
yeah,
I think we need to take a closer look at the mathematical machinery behind these findings.
Okay.
In our next segment, let's delve into some of the key lemmas and propositions that underpin these results.
That sounds good. I'm ready.
Awesome. I'm excited to keep going.
All right. So let's delve into some of those mathematical details.
Okay.
Remember those critical points, the points where the derivative of our function is 0?
Right. Those are like the pivotal points on a roller coaster.
Exactly.
Where you feel that change in motion the most.
Yeah, they play a crucial role in understanding the dynamics of these generalized McMullen maps.
Okay.
Lemma 3.1 actually gives us a precise formula for these critical points.
Okay, so what does it tell us?
It tells us that the critical points of R sub NAC are given by G sub K equals the magnitude of A to the 1 over 2n's times e to the I times the quantity pi plus 2k pi closed quantity over 2n.
Wow, okay.
Where k ranges from 0 to 2n minus 1 and psi is the argument of a c.
Okay.
Essentially, these critical points are distributed around a circle in the complex plane.
Okay, so I'm picturing...
Their location depends on both the magnitude and argument of the parameter, like beads on a necklace.
Right, and they're kind of spaced out evenly.
Exactly.
But how do these critical points relate to the overall behavior of the map?
Well, the lemma goes on to establish a fascinating connection.
Right.
It tells us that the critical points with even indices map to the critical value V plus, which is C plus 2 root n, while the critical points with odd indices map to the critical value V minus, which is C minus 2 root A.
So we've divided these critical points into two groups.
Exactly.
Each is kind of drawn to a specific critical value.
Right, there's a nice symmetry in that.
Now remember you mentioned these special sets, U prime sub AK and U plus or minus sub A.
Yes.
Can you remind us how those are defined and why they're so important?
Certainly. So Definition 3.2 introduces U prime sub AK as a polar rectangle in the complex plane.
Okay.
It's defined as the set of all complex numbers Z, such that the magnitude of Z lies between the magnitude of A to the 1 over n all over 2 and 2, and the argument of Z is within pi over 2n of the quantity psi I plus 2k pi plus quantity all over 2n.
So we're essentially carving out specific wedge-shaped regions.
Yes, you can think of it that way.
In the complex plane.
Exactly.
These are our starting point for analyzing the map's behavior.
Right.
And what about the sets, U plus or minus sub A?
So U plus sub A is simply the image of U prime sub A 0 under the map R sub NA. And similarly, U minus sub A is the image of U prime sub A 1.
So we're watching these regions morph and change as they journey through this mathematical landscape.
Yeah, that's a great way to put it.
Defined by the map.
Yeah.
What's the significance of these sets?
So that's where things get interesting. Proposition 3.4 reveals that both U plus sub A and U minus sub A turn out to be halves of an ellipse.
Hold on. We start with these wedge-shaped polar rectangles.
Right.
Apply the map, and we get these smooth elliptical shapes.
It's pretty remarkable.
That's fascinating.
It is.
So we begin with these angular shapes, apply the map, and suddenly these graceful ellipses emerge.
Yeah, it's like watching origami unfold mathematically.
What can you tell us about these ellipses?
They have some special properties. The proposition clarifies that this ellipse, denoted by E, is centered at the parameter C and is rotated by an angle of psi I over 2.
So the parameters of our map directly influence the position and orientation of this ellipse.
That's right.
It's like these parameters are the puppet masters.
Yeah, good analogy.
Orchestrating this whole geometric show.
It is a show.
What about the foci of these ellipses?
The foci are actually very significant. The foci of this ellipse are precisely the two critical values, V plus and V minus, which are the points that attract those groups of critical points.
Everything's interconnected.
It is, beautifully.
The critical values determine the foci of the ellipse, which emerges from transforming these polar rectangles.
Yeah, it's a really elegant structure.
Now, can you remind me why we needed to establish an escape radius?
Sure.
For these generalized McMullen maps? I know it has to do with orbits, but I'm a little fuzzy on the details.
So the escape radius is a crucial concept for understanding the long-term behavior of orbits under these maps. It stems from the fact that for n greater than or equal to 2, the point at infinity acts like a powerful magnet, drawing in orbits that venture too far from the origin.
So once an orbit crosses a certain threshold, it's inevitably pulled toward infinity.
That's a great way to put it, yeah.
Like an event horizon.
Exactly.
Beyond which there's no turning back.
That's right.
And because of this pull towards infinity, each Julia set must be bounded.
Precisely. They can't stretch out to infinity because of that attracting force.
They're confined within a celestial boundary.
Yeah, I like that.
How does this escape radius help us understand these boundaries?
Well, Lemma 3.5 gives us a way to calculate this escape radius, beyond which we can guarantee that any orbit will escape to infinity. This radius, denoted by S in the lemma, is determined by taking the maximum of 4, the magnitude of C, and the magnitude of A.
So the escape radius depends on the parameters of our map.
Yes.
It adjusts to the specific landscape we're exploring.
Exactly.
There's also this forbidden zone around the origin.
You're absolutely right.
That we need to consider.
That's right. Yes.
So tell me about that.
Lemma 3.6 introduces this forbidden zone. It tells us that any orbit starting within a radius of t, which is equal to the magnitude of to the 1 over n, all divided by s, will also escape to infinity, even though it's close to the origin.
So we have this outer boundary beyond which orbits escape. And an inner boundary within which orbits also escape.
Exactly.
It's like we built this mathematical fence.
Yeah, I like that.
With two layers. Trapping these interesting dynamics in between.
Exactly.
By combining these two lemmas, we get proposition 3.7, which states that the filled Julia set must be contained within the annulus.
That's right.
AT.
Yes, so we've effectively corralled the filled Julia set, confining it to that ring-shaped region.
So we've laid out these foundational concepts, these critical points, their connection to the critical value, the special sets. U prime sub AK and U plus or minus sub transforming into ellipses. The idea of this escape radius and this forbidden zone. But how do all these pieces fit together to actually prove Theorem 1?
That's a great question. That's where the real elegance of this research comes in.
Okay.
The proof of Theorem 1 weaves together all these ideas, using a series of lemmas and propositions to build a solid mathematical argument. Okay. Are you ready to unravel that argument?
Absolutely. Lead the way. Yeah. Okay, let's tackle this proof of Theorem 1.
All right.
It promises us n baby Mandelbrot sets in the A-plane.
Yes.
For those generalized McMullen maps, when the magnitude of C is greater than or equal to 6, and n is sufficiently large.
That's right.
I'm ready to see how these mini-m's emerge from the equations.
So it's a beautifully constructed proof that cleverly uses the concept of polynomial-like mappings.
Okay.
These mappings allow us to relate our more complicated generalized McMullen maps back to those familiar quadratic polynomials and the classic Mandelbrot set.
It's like finding a hidden bridge that connects these two seemingly different worlds.
Exactly. That's a great way to think about it.
And I remember you mentioning that polynomial-like maps essentially provide those baby Julia sets in the dynamical plane.
Right.
First, acting as stepping stones to those baby Mandelbrot sets in the parameter plane.
Exactly.
So the researchers strategically focus on identifying those special values where a critical point actually becomes a fixed point.
Right.
These fixed critical points act as the centers of our potential baby Mandelbrot sets.
That's right, like marking spots on a treasure map.
But how do we actually capture those baby Mandelbrot sets mathematically?
So to capture those baby Mandelbrot sets, we define those regions called W sub C.
Okay.
Each centered around one of those fixed critical points.
Okay, so those are our hunting grounds.
Exactly.
The places where we expect to find the mini-m's.
Precisely.
But how do we know for sure that those regions actually contain baby Mandelbrot sets?
The key lies in demonstrating that within each W sub C, J, the generalized McMullen map, behaves like a quadratic polynomial on a specific subset of its domain that U prime sub A, epA. This is where things get a bit more technical.
I'm ready.
Okay, so to establish this polynomial-like behavior, we embark on a series of carefully crafted lemmas.
Okay.
First lemma 4.12 assures us that for sufficiently large n, a specific disk, D0, 2, is always contained within the ellipse E.
Oh, that ellipse we were talking about earlier.
Exactly.
What's the significance of this disk being inside the ellipse?
Well, this containment in turn means our special polar rectangles, those U prime sub AKs, are also snugly inside E for all A values within a W sub CJ region.
Okay, so we've got our sets neatly contained.
Yes.
What's the next step?
The next hurdle is to prove that U prime sub AK is also contained within its image under the map, which is U sub AK. This is where we need to make sure things don't spin out of control.
Spin out of control.
As we move around in the parameter space.
Tell me more about this spinning.
Okay, so it all boils down to the argument of the critical points. And how it changes as we move around within a W sub C J region.
Lemma 4.13 demonstrates that this change in argument is bounded by a specific value pi over 2n.
So we're keeping those critical points on a tight leash, preventing them from wandering too far.
Yes. This bound on the change in argument is crucial for lemma 4.14, which finally establishes that U prime sub A, K is indeed contained within its image U sub AK for all A within the W sub CJ region.
So we've finally shown that these sets are nested the way we need them to be.
We have. And with the sets properly nested, we arrive at proposition 4.15, which triumphantly declares that our generalized McMullen map is indeed polynomial-like of degree 2 on each of those special sets, U prime sub A, K for every A within a W sub CJ.
So we've satisfied that crucial condition for polynomial-like maps.
Yes, we're almost there.
What's next?
We need one final piece of the puzzle
to
show that as we trace a path around the boundary of a W sub C J region, the critical value winds once around the corresponding critical point.
We need that lasso.
We do. Can you remind me why it's so important that this winding number needs to be exactly 1?
It ensures that our map truly captures the essence of the quadratic polynomial that gives rise to the Mandelbrot set. This winding number being 1 is a hallmark of the quadratic-like behavior we're looking for.
So it's not just about being polynomial-like. It's about having the right kind of twist as we go around that boundary.
Yeah, it's like we're choreographing a mathematical dance.
And lemma 4.16 demonstrates that this crucial winding behavior does indeed occur.
It does.
So with all these lemmas and propositions, we finally built up all the necessary machinery to prove Theorem 1.
We have.
What does that final step look like?
The final step is where everything beautifully converges.
Okay.
We invoke the straightening theorem for polynomial-like maps.
Okay.
This theorem, a powerful tool in complex dynamics, essentially tells us that if a map behaves like a polynomial in a certain region, then it can be straightened out to look exactly like that polynomial.
So we're taking that local resemblance to a quadratic polynomial, making it global.
Exactly.
Okay.
And because our generalized McMullen map is polynomial-like of degree 2 on each U prime sub A, K within a W sub C, J region, the straightening theorem tells us that each W sub C, J region must contain a homeomorphic copy of the Mandelbrot set.
So by carefully dissecting the behavior of these generalized McMullen maps, we've revealed the existence of n miniature Mandelbrot sets hidden within their parameter spaces.
It's really quite beautiful.
It is.
How it all comes together.
We started with these somewhat abstract functions. And through a series of precise mathematical steps, arrived at these stunning fractal structures.
It is a testament to the power of mathematical analysis.
It's definitely been a mind-bending journey.
It has.
But thanks to your expert guidance,
of course,
I feel like I successfully navigated through this dense research.
I think you did a great job.
And come out the other side with a newfound understanding.
Well, the pleasure was all mine.
Though that wraps up another deep dive.
It does.
Into the fascinating world of mathematics.
Indeed.
We hope you've enjoyed exploring the intricate realm of baby Mandelbrot sets.
I hope so.
And the elegant mathematical tools.
That's beautiful stuff.
That allow us to unravel their secrets.
It is.
Until next time, keep exploring, keep questioning, and keep diving deep into that vast ocean of knowledge.
That's good.
Get ready for a deep dive into a pretty fascinating area of math. Baby Mandelbrot sets. We'll be looking at excerpts from a research paper with a really long title. Baby Mandelbrot sets and spines in some one-dimensional subspaces of the parameter space for generalized McMullen maps.
Sounds like fun.
Yeah, it's going to be pretty cool. You might be surprised to learn that the famous Mandelbrot set has, well, babies.
Mandelbrot babies.
Yeah. And we're going to figure out where these babies live and what they can tell us about the bigger picture.
It's kind of like finding a secret world within the already intricate world of fractals. Tiny Mandelbrot sets hidden within a larger structure.
Exactly. But before we get too far ahead of ourselves, let's start with the basics. The Mandelbrot set itself. For our listeners who might need a quick reminder, how would you define the Mandelbrot set?
Okay, imagine you have a really simple process. You start with a complex number. Let's call it z. We'll initially set it to 0.
Got it.
And then you just repeat this rule over and over. Square z's and then add a constant c as another complex number. The Mandelbrot set is just the collection of all those c values, where this process doesn't explode to infinity.
So all the c values that stay bounded.
Exactly.
It's always amazing to me how such a simple rule can create such complex and beautiful shapes.
Right. And they're not just pretty pictures either. They actually tell us a lot about how this iterative process behaves.
It's like a visual representation of where order and chaos meet.
Exactly. And within this world, we have other important sets like the Fatou and Julia sets.
Yes.
Yeah, forget about those.
They give us even more insight into how these iterative processes work.
Yeah.
The Fatou set represents the stable regions, while the Julia set is all about chaos.
Right. Small changes in the initial conditions can lead to drastically different outcomes in the Julia set.
Exactly.
Now, the paper we're looking at today focuses on a family of functions called Generalized McMullen Maps. These functions are a bit more complex than the simple z squared plus c, but they still have some key characteristics that make them really interesting to study. Yeah, these generalized McMullen maps look like this. Rn, A, C, Z, Zn plus A, Zn plus C has to be a positive integer that's greater than or equal to 3. And then A and C are complex numbers. A can't be 0.
Okay, so instead of a single constant C, like in the classic Mandelbrot set, we now have two variables, A and C.
Right.
Which obviously makes things a lot more complicated.
It does, but it also makes it much more interesting. The beauty of these maps is that they have two free parameters, A and C, And they have two NFL critical points that map to two critical values. We'll call them V plus and V.
So those critical points and values are they kind of like landmarks on our mathematical map.
Right.
Guiding us toward those baby Mandelbrot sets.
You got it. They're essential for understanding how these maps behave. The researchers use computer-generated images to visualize this complex landscape.
So it's like we have a visual representation of this multidimensional space.
Right. Each image uses different colors to represent the orbits of the two critical values.
Like a treasure map.
Oh.
Leading us to the hidden gems.
Exactly. The baby Mandelbrot sets.
So how do we actually find these babies hidden within this incredibly complex landscape?
The key is this concept called polynomial-like maps.
Okay.
These are maps that within certain regions behave a lot like simpler polynomials, like the one that defines the classic Mandelbrot set.
So we're looking for areas where these complicated functions simplify a bit.
Exactly. The paper focuses on two sets, U prime and U, that are key to establishing this polynomial-like behavior.
It's like we have this super detailed map of a huge city, and we're using a magnifying glass to zoom in on specific neighborhoods.
I like that analogy.
We're focusing on particular regions within the complex plane where those familiar Mandelbrot patterns might pop up.
Precisely. The paper also introduces what they call polar rectangle sets. They denote them as U prime sub a k, and then their images under the map are denoted as U plus sub a and U minus a sub a. They also discuss an ellipse E and how it connects to those critical values we talked about before. Visualizing these shapes and how they relate to each other is essential for understanding the concept of containment and mapping within this dynamical system.
Okay. Now, the paper mentions an escape radius for RNA-C. What exactly does that mean in this context, and why is it so important?
Think of the escape radius as a boundary. If the orbit of a point under iteration goes beyond this radius, it's going to zoom off to infinity.
So it's like a point of no return.
Exactly. The concept of a bounded neighborhood for the filled-Julia set ensures that all the points inside this neighborhood will stay bounded under iteration.
So we're setting up these boundaries to help us identify those regions where the behavior of the generalized McMullen map starts to look like a simpler polynomial.
Right, and that's where we might find those baby Mandelbrot sets.
And this is where things get really cool. The paper says that under specific conditions, certain U prime sub-day sets stay completely contained within their images.
Yes, and that creates what we call baby Julia sets.
Baby Julia sets. Wow.
And those baby Julia sets are the foundation for the emergence of those baby Mandelbrot sets in the parameter plane.
It's fascinating how these smaller structures inherit those complex and beautiful characteristics of the original Mandelbrot set.
It really is. It shows just how intricate these mathematical systems can be.
So the research mainly focuses on cases where the absolute value of C is greater than one hit.
Right, right. They show that under these conditions, baby Mandelbrot sets exist within the A-plane. They introduce specific regions, denoted as W sub Cj, and they describe the conditions that lead to the formation of these baby Mandelbrot sets, which they often call baby M's.
So by carefully analyzing the parameter space defined by A and C, we can actually pinpoint the locations of these hidden baby Mandelbrot sets.
Exactly.
It's like a mathematical treasure hunt.
I like that.
Now let's talk about those diagonal slices of the parameter plane where C is proportional to A. So we can write that as C, where T is a constant.
Right.
The researchers introduced this idea of a spine, which they denote as S sub T. This is the set of all A values that satisfy a certain equation. The absolute value of t plus or minus 2 times the square root of a equals 1. This spine acts like the backbone of the boundedness locus within these diagonal slices. It's like it's outlining the boundaries where baby Mandelbrot sets are allowed to exist.
So the spine helps us narrow our search.
Exactly. And the research paper actually claims that the entire boundedness locus for a given tes value always stays within a certain distance epsilon of this spine.
Right. It's like the spine is a magnet pulling the boundedness locus towards it.
Exactly. This systematic approach to unraveling these complex structures is just amazing. It's like solving a giant jigsaw puzzle, one baby Mandelbrot set at a time, guided by these spines and boundaries.
It is. And it gets even more interesting from here.
I bet it does. But I think it's time for us to take a little break. We'll come back and explore those diagonal slices in more detail in the next part of our deep dive.
Sounds good.
Welcome back to our exploration of baby Mandelbrot sets. Last time we got a good overview of generalized McMullen maps and introduced the idea of these smaller Mandelbrot-like structures hiding within those maps.
Right.
We even talked about the importance of diagonal slices where C is proportional to A and how this special curve called the spine guides our exploration.
Right. Now we're ready to dig a bit deeper into the math behind all of this those diagonal slices where C equals ta. They're just packed with these tiny Mandelbrot-shaped regions.
They are.
But before we get lost in all of that, we need to really understand this idea of the spine, that backbone of the boundedness locus within these slices.
You mentioned before that the spine, denoted as S sub t, is defined by a specific equation. The absolute value of te plus or minus 2 times the square root of a equals 1. I get the equation, but what does it actually represent? And why is it so important for understanding these baby Mandelbrot sets?
Okay, let's break that down. This equation basically tells us which a values in the parameter plane will make at least one of the critical values of our generalized McMullen map land right on the unit circle in the complex plane.
So it's kind of like highlighting those special a values.
Exactly. And remember, those critical values are like signposts. They guide how the whole system behaves.
I'm still a little confused about the importance of the unit circle. Why does it keep popping up in our discussion?
Great question. The unit circle is super important in the dynamics of these systems. For larger in values in our generalized McMullen map, the Julia sets tend to cluster around the unit circle.
Yeah.
So if a critical value also happens to be on or near that unit circle, it's more likely that its orbit will stay bounded. And that's when we start to see those interesting Mandelbrot-like structures.
So the spine helps us identify those a values where boundedness is more likely.
Yeah.
And you said earlier that the entire boundedness locus for a given 10 value stays within a certain distance epsilon of this spine.
Right. That's what Theorem 2 in the paper is all about. It says that for any epsilon, no matter how small, we can always find a big enough bun so that the whole boundedness locus stays within an epsilon neighborhood of the spine.
It sounds like a really complicated theorem to prove.
It is a bit involved, but the main idea is actually pretty elegant. The proof uses two main tools. First, they use corollary 2.4 from the paper, which basically says that for any complex number C and A and any epsilon, we can always find a large enough n so that the filled Julia set of our generalized McMullen map fits inside a thin ring or annulus centered at the origin.
Yeah.
The inner and outer radii of this ring are 1 minus epsilon and 1 plus epsilon, respectively.
So as n gets bigger, all the interesting stuff happens really close to that unit circle.
You got it. Now here's where the second tool comes in. They combine geometric arguments with the definition of the boundedness locus.
The boundedness locus is just the collection of all the a values, where at least one of the critical orbits stays bounded, right?
Right. Now imagine we have an a value that's not within epsilon of the spine. This means both of its critical values are farther than epsilon away from the unit circle.
Okay, so they're kind of like outliers.
Yeah. Now remember corollary 2.4? Well, they use that to argue that for a large enough in the filled Julia set is so tightly clustered around the unit circle that those critical values being more than epsilon away can't possibly be inside it.
They're too far away to be part of the action.
Exactly. And if those critical values aren't in the filled Julia set, their orbits can't be bounded either. They're free to escape to infinity.
Which means our original a value can't be part of the boundedness locus.
Exactly. So any a value that's more than epsilon away from the spine can't be in the boundedness locus. That means the whole boundedness locus has to be within that epsilon neighborhood of the spine.
It's like the spine is setting a boundary.
That's a great way to think about it. This whole argument shows how beautifully connected these concepts are. The geometry of the filled Julia sets the definition of the boundedness locus and the equation of the spine all come together.
So where do we go from here? We know where these baby Mandelbrot sets might be, but how do we actually find them?
Well, the paper gives us some hints. They suggest using lemma 2.5, which gives us a way to find those special a values where a critical point maps directly onto itself.
So we're looking for those points where things stay put.
Exactly. And when we're working with those diagonal slices where C equals te, we need to solve this modified equation. W to the n minus 1 power minus 2 times W to the 10 minus 1 power divided by T equals 0 W represents the fixed point.
Okay. So we have to do some algebraic gymnastics to solve for W.
Right. And once we've found these potential centers, we need to construct those special regions like the W sub Cj sets we mentioned before.
Those regions are like little nurseries for the baby Mandelbrot sets.
Exactly. And to prove that we actually have a polynomial-like map of degree 2 within each of those regions, we need to show two things. First, that U prime is completely inside U, and second, that U prime is relatively compact in U.
So U prime has to fit inside U with a little bit of wiggle room.
Exactly. The paper has a bunch of lemmas that build on each other to prove that this containment actually happens.
That sounds really intricate.
It is. But the basic idea is that they start by showing that for any a value inside one of those W sub Cj regions, the entire disk of radius 2 centered at the origin is inside the ellipse. This is important because U prime, our polar rectangle, is always inside that disk.
Okay, so U prime is definitely inside the ellipse.
Right. Then they prove that U prime never touches the minor axis of the ellipse. They do this by showing that U prime is inside a circle centered at the right critical value with a radius smaller than the distance from that critical value to the minor axis.
It sounds like they're being really careful about where they put U prime.
They are. This careful placement makes sure that U prime stays completely within one half of the ellipse, the half that matches up with its image U under the Generalized McMullen Map.
So they've established a clear path from U prime to U.
Exactly. But there's one more thing. We need to show that as A moves around the boundary of W sub Cj, the image of the critical point inside U prime winds around that critical point once. This image has to stay inside U but never go back into U prime.
So we're basically tracking the movement of that critical point's image.
Right. And this winding behavior ensures that the mapping between U prime and U behaves just like a quadratic polynomial. That familiar z squared plus c that gives us the classic Mandelbrot set.
It's like a little dance.
Yeah, it's a topological requirement, like a mathematical rule that guarantees those Mandelbrot shapes will appear.
The paper must go into a lot of detail to prove all of this.
It does. They very carefully analyze the boundaries of W sub Cj and the paths traced by the critical value. They want to be absolutely sure that the mapping follows the rules.
So they've proven that within each of these W sub Cj regions, the generalized McMullen map acts just like a quadratic polynomial.
Exactly. And that brings us to the main point, the conclusion that each of those W sub Cj regions contains a homeomorphic copy of the Mandelbrot, set a tiny Mandelbrot-like structure.
That's incredible. They've taken this complex map and found these pockets of simplicity within it.
And it's all thanks to math. Careful reasoning, clever arguments, and elegant proofs that show us the connections in these abstract worlds.
This deep dive has been amazing. We started with a simple question. Does the Mandelbrot set have babies? And through all of this exploration, we found a definitive answer. Yes.
And it's been a fantastic journey getting here.
It feels like we've just scratched the surface, though.
Yeah.
What else is there to discover about these baby Mandelbrot sets?
Oh, there's so much more. This research opens up all sorts of new avenues for exploration. We've only just begun to understand these baby Mandelbrot sets and what they mean for the field of complex dynamics. Who knows what other mathematical treasures are out there waiting to be found?
It's exciting to think about.
Absolutely.
Welcome back to our deep dive into the world of baby Mandelbrot sets. In the last two parts, we explored this really cool idea of miniature Mandelbrot-like structures hiding within the parameter space of generalized McMullen maps. We talked about those diagonal slices where C is proportional to A, and how this special curve we call the spine acts like a guide for our exploration. We even went through the proof of Theorem 2, which showed us how the boundedness locus sticks close to that spine, setting the boundaries for where those baby Mandelbrot sets might exist.
Right, and now we're going to get into the nitty-gritty of the math that proves those baby Mandelbrot sets actually exist, especially when we're dealing with larger C values.
I'm ready to see how it all comes together. Where do we start?
Okay, so let's focus on cases where the absolute value of C is greater than or equal to 6, and we'll assume n is big enough. Specifically, we want n to be large enough that 4 times the absolute value of C plus 8 is less than 2 to the n plus 1 power. This makes sure we're in a region of the parameter space where those baby Mandelbrot sets are really prominent.
So we're zooming in on a specific area where things get interesting.
Exactly. And in this region, we're going to focus on those special regions, W sub Cj. Remember, we can think of them as nurseries for our baby Mandelbrot sets.
Right. You mentioned before that these W sub Cj regions are bounded by specific curves that are defined in terms of C and A. Could you refresh our memory on what those curves look like and why they're so important for those baby Mandelbrot sets to form?
Sure. Each W sub Cj region is kind of shaped like a distorted disk. Its boundaries are defined by 4 different curves. The inner and outer boundaries are almost circular, and they're determined by setting the modulus of the critical values, the absolute value of C plus or minus 2 times the square root of A equal to 12 and 2, respectively.
So these boundaries mark those A values where the critical values are a specific distance from the origin.
Exactly, like setting up a fence around our nursery. And then we have those ray-like boundaries. They're arcs of parabolas, and they're determined by fixing the argument of those critical values, C plus or minus 2 times the square root of a value, to match the argument of a specific fixed critical point, which we'll call W sub j plus or minus pi over 2n.
Okay, so we're controlling both the distance and the angle of those critical values. It sounds pretty precise. How does all of this lead to the formation of those baby Mandelbrot sets?
Well, the key is that within each W sub Cj region, we can construct those special sets, U prime and U, that give us that polynomial-like behavior we need for those Mandelbrot-like structures to appear. Remember, U prime is that carefully chosen polar rectangle centered on a critical point, and U is its image under the generalized McMullen map.
I'm picturing those polar rectangles snuggled inside those W sub Cj regions like seeds in a garden.
I like that. Now, to prove that we have a polynomial-like map of degree 2 within each of those W sub Cj regions, we have to show two things. First, that U prime is completely contained within U, and second, that U prime is relatively compact in U.
So U prime has to fit inside U, but not touch the edges.
Exactly. It needs some breathing room. The paper goes through a bunch of lemmas to prove that this containment actually happens. It starts by showing that for any A value inside a W sub Cj region, the entire disk of radius 2 centered at the origin is inside the ellipse E. This is important because our polar rectangle U prime is always contained within that disk.
So step 1, make sure U prime is inside the ellipse.
Right. Then they prove that U prime never intersects the minor axis of that ellipse. They do this by showing that U prime is inside a circle centered at the right critical value with a radius that's smaller than the distance from that critical value to the minor axis.
So they're carefully positioning U prime to make sure it doesn't cross that dividing line within the ellipse. Why is that separation so important?
It guarantees that U prime is completely within one half of the ellipse, the half that corresponds to its image. U under the generalized McMullen map. So we have a clear mapping between U prime and U.
So they've used the geometry of those sets, the disk, the ellipse, the circle, and the polar rectangle, to make sure everything lines up perfectly.
Precisely. But there's one more piece to this puzzle. We need to show that as the parameter A moves around the boundary of W sub Cj, the image of the critical point inside U prime winds around that critical point once. This image has to stay within U the whole time, but it can't go back into U prime.
So we're tracing the movement of that critical point's image. Why is that winding behavior so important?
It ensures that the mapping between U prime and U behaves the same way as a quadratic polynomial, that z squared plus c that gives us the classic Mandelbrot set. It's a topological requirement, like a mathematical dance move that guarantees those Mandelbrot shapes will show up.
It's amazing how they've thought of everything.
The paper goes into a lot of detail to prove this winding behavior. They analyze the boundaries of W sub Cj and the paths traced by the critical value. They leave no room for doubt.
So they've proven that within each of these W sub Cj regions, the generalized McMullen map acts just like a quadratic polynomial.
Yes, and that leads us to the big conclusion. Each of those W sub Cj regions contains a homeomorphic copy of the Mandelbrot set, a tiny Mandelbrot-like structure hiding within this complex mathematical world.
It's like finding a hidden treasure. They've taken this incredibly complex map and found these pockets of simplicity within it.
And it's all thanks to the power of math. Careful reasoning, clever arguments, and elegant proofs that help us see the connections in these abstract worlds.
This has been an incredible deep dive. We started with a simple question: does the Mandelbrot set have babies? And we found a definite answer: yes. But we've also discovered so much more along the way. We've learned about generalized McMullen maps, diagonal slices, spines, and those fascinating W sub Cj regions. It's been a real journey of exploration.
It has. And the beauty of it is that there's still so much more to explore. We've only just scratched the surface. There's a whole universe of mathematical wonders out there just waiting to be discovered.
That's what makes math so exciting. Thank you for joining us on this deep dive into the captivating world of baby Mandelbrot sets. We hope you've enjoyed the journey and maybe even feel inspired to explore some of these ideas on your own.
Thanks for having me.
Welcome to our deep dive, and we're going to be looking at baby Mandelbrot sets.
Ooh, interesting.
Yeah. So the paper that we're going to be looking at is Baby Mandelbrot Sets and Spines by Suzanne Boyd and Matthew Hoeppner. Have you heard of baby Mandelbrot sets?
I have. They're, I think of the Mandelbrot set as a visual representation of what happens when you repeat a certain math equation over and over and over again. And
Right.
and sometimes those images have a tiny replica of the whole set within them.
Exactly. Yeah, and they're really kind of amazing. I mean, if you think about it, so what we're talking about here is the Mandelbrot set is this visualization of a mathematical equation, and these tiny perfect replicas are embedded within the larger Mandelbrot set.
Yeah.
And so what Boyd and Hoeppner are really doing is they're trying to explore how these baby Mandelbrot sets form. Where do they, under what conditions do these miniature replicas actually appear?
Yeah, and what's so cool about their work is that they're not just saying, here's the Mandelbrot set, and here are some baby Mandelbrot sets that we found. They're actually looking at a very specific, I guess you could say, slice or area of a broader mathematical space and figuring out what leads to these baby Mandelbrot sets in that region.
Right. So it's like they're exploring very specific mathematical conditions that give rise to these miniature Mandelbrot sets.
Okay.
And they're looking at how those conditions influence the shape and the location of these baby Mandelbrot sets within the larger Mandelbrot set.
Right. So it's almost like, you have this vast mathematical wilderness, and they're kind of carving out a very specific path and saying, okay, in this area, this is what leads to these really cool features.
Exactly. So how do they even begin to approach this problem? I mean, where do they even start?
Well, it all starts with the concept of the boundedness locus. When we're talking about iterating these equations that generate the Mandelbrot set, some of the values that we plug in will stay bounded. They'll create those beautiful, intricate shapes that we see, but other values will just kind of fly off to infinity. And the boundedness locus is like a map that tells us, okay, which parameters in our equation lead to those nice, stable, bounded patterns, and which ones lead to this kind of chaotic behavior where things just explode and go off to infinity.
Yeah, it's like a guide to finding those little pockets of order and stability within this vast mathematical universe.
Right, exactly. And to actually visualize these intricate patterns, to actually see them, mathematicians use computers and specific algorithms to assign colors to different points. And so these algorithms, basically, they look at how quickly a point escapes to infinity when you plug it into the equation.
Yeah.
And that determines the color that it gets assigned.
Right.
And then all of a sudden you have these stunning visual representations of the Mandelbrot set and all of its complexities.
Right. So each color is basically telling a story.
Yeah.
About the fate of a specific point.
Yeah.
Whether it stays bounded and creates this, intricate, beautiful pattern, or whether it just kind of, flies off into chaos.
Exactly. Yeah. It's almost like you're seeing, different destinies play out right in front of you.
Right. It's amazing. But how do these baby Mandelbrot sets, these tiny perfect replicas, how do they actually come about?
Right. That's a great question. And to understand that, we have to go back to the groundbreaking work of the mathematicians Dewey and Hubbard.
Okay.
And they explored these things called polynomial-like maps. And what they discovered is that sometimes these very complex mathematical functions, if you look at them in very specific regions, they can actually behave like simpler polynomial functions. Right. So it's like you're zooming in on a tiny part of this complex map, and you realize, oh, this looks familiar. This looks like something we've seen before.
Right.
And this discovery is absolutely key to understanding how those miniature Mandelbrot replicas form. Because it turns out that those baby Mandelbrot sets are actually arising from these polynomial-like maps.
So it's like finding a familiar landmark, like a lighthouse or something, within a vast uncharted territory.
Exactly. Yeah.
And you can use your knowledge of that landmark to kind of orient yourself and understand the surrounding landscape.
Yeah. A perfect analogy.
So it's just amazing that they're able to connect these seemingly complex mathematical functions to these simpler polynomial functions.
Yeah. And in this paper, Boyd and Hoeppner, they focus on a very specific equation. And it looks like this: Rn ACZ ZM plus A, ZM plus C, where n is greater than or equal to 3. And what they're really interested in is exploring what happens when you tweak those parameters, A and C. It's almost like you have these dials that control the shape and the behavior of the patterns that you get.
Right.
And they're trying to figure out, okay, what combination of A and C will lead to the formation of these baby Mandelbrot sets?
It's like they're exploring different regions within this mathematical space.
Yeah.
By adjusting those dials and seeing what kind of patterns emerge.
Exactly. And to understand their findings in more detail, we need to introduce a couple of key concepts.
Okay.
First, there's the idea of an escape radius.
Right.
And basically, this is a boundary beyond which any number that you plug into this equation will just inevitably fly off towards infinity.
So if it crosses that boundary line, it's basically, saying goodbye to the world of boundedness and hello to chaos.
Exactly. Yeah, it's like reaching the point of no return.
Right. So this escape radius is really important for identifying those bounded patterns that make up the Mandelbrot set and its babies.
Exactly. And then another important piece of the puzzle is what they call this elliptical region, which they denote by E.
Okay.
And this ellipse plays a really crucial role in kind of determining where those baby Mandelbrot sets are going to reside. And the size and the shape of this ellipse are directly influenced by those parameters, A and C, that we were talking about earlier, those control dials.
Oh, I see. So it's like a container, or at least a region where these baby Mandelbrot sets might be found.
Yeah. Think of it as, you're looking for something specific, and they're saying, okay, we know it's going to be in this general area.
Right. Okay.
And then there are also these special points, kind of fixed critical points, and these are kind of like the centers of those baby Mandelbrot sets. They're points that even after you apply the equation to them over and over again, they stay the same.
So they're like the anchors of these miniature universes.
Exactly.
I like that.
Yeah, they're kind of the stable points around which all of this complexity is swirling.
Right.
And in their paper, Boyd and Hoeppner, they actually explore two different scenarios depending on the value of C. So first, they look at what happens when C is small.
Okay.
And in this case, they find that these baby Mandelbrot sets are located within a specific polar rectangle, which they denote by UAN. And this rectangle has a very specific position relative to that ellipse D that we talked about, and some other important points called critical values, which are denoted by V plus and V.
Okay, so they've kind of narrowed down the search area for these hidden gems.
Right. They're saying, okay, if C is small, we know we can find these baby Mandelbrot sets within these specific regions.
Right.
And then for larger C's values, they define these regions in the A-parameter plane, denoted by WCJ, where these baby Mandelbrot sets reside. And they use some very clever geometric arguments and the behavior of those critical values, the V plus and V, to actually prove that these miniature Mandelbrot sets exist within these WCJ regions.
Oh, wow. So they've actually proven mathematically that these miniature Mandelbrot sets exist under these specific conditions.
Exactly, yeah.
Yeah.
That's amazing. So, they've kind of laid out this map, if you will, to where these hidden mathematical treasures can be found.
Right. Okay, but before we get too deep into the specifics of their proofs, you mentioned polar rectangles. Can you just remind me what those are?
Absolutely. So a polar rectangle is basically a region in the complex plane where you describe points by their distance from the origin, which is what we call the radius, and their angle from a reference line, which is called the argument. So you can think of it like a slice of a pie, where the radius determines how far out you go from the center of the pie, and the argument determines which slice of the pie you're looking at.
Right. So it's basically a way of defining a region within the complex plane using these polar coordinates.
Exactly. Yeah, exactly. And so each of these UA rectangles, it's like a wedge-shaped slice of a ring centered around a specific angle, and that angle is determined by A and N. And what Boyd and Hoeppner do is they show that under certain conditions, the function, RNAC, maps this UA rectangle onto a larger region, which they denote by UA in a very specific way.
Okay, so they're basically showing that this smaller region gets mapped onto this larger region.
Yeah, and this mapping is really important because it's what makes the function behave like a simpler polynomial within that region. It's like you're taking this really complex multidimensional shape and you're projecting it onto a simpler two-dimensional plane that we can analyze it more easily.
So it's like we're zooming in on a small section of this complex landscape, and we find that it actually looks a lot like familiar territory.
Exactly.
Okay, I like that.
Yeah, and to prove that a function is polynomial-like, they have to show that this mapping from the smaller region to the larger region has a few key properties. It has to be what we call proper, which means that points near the boundary of the smaller region get mapped to points near the boundary of the larger region. And it also has to be what we call analytic, which means that it's smooth and well-behaved. It doesn't have any jumps or breaks.
So it's like making sure that the mapping doesn't create any distortions or weird folds in our mathematical fabric.
Exactly, yeah. It needs to be nice and continuous.
Okay.
And once they've established that the function is polynomial-like within these regions, then they can unlock all of these powerful mathematical theorems that help us understand how the function behaves and how those baby Mandelbrot sets form.
So it's like they're using these polynomial-like maps to kind of tame the complexity of this equation,
right,
and pinpoint the locations of these baby Mandelbrot sets.
Exactly, yeah.
Okay.
And to do that, they have to really delve into the critical points of the equation, which are the points where the derivative of the function is 0.
Okay. So are we ready to go down this mathematical rabbit hole and look at how they analyze these critical points?
I think we are.
Okay.
Let's do it.
Yeah, let's do it. Okay, so let's jump into how they analyze these critical points to prove that these baby Mandelbrot sets exist.
Right.
So remember how we were talking about those WC regions? Mm-hmm. Those are the areas in the parameter plane where they suspected the baby Mandelbrot sets might be hiding.
Right.
And to construct these regions, they use 4 curves.
Okay.
2 to define the inner and outer boundaries of the region.
Okay.
And then 2 more to form the sides.
Yeah.
So the first 2 are basically like defining a ring or donut shape in the parameter plane.
Yeah, exactly like a donut.
Okay.
And the WCJ region lies within that donut.
Okay, and how are those boundaries determined?
Well, they're defined by setting the modulus of a critical value, either te plus timia or tactinia, equal to certain values.
Okay.
So for the inner boundary, that modulus is set to 12.
Okay.
And for the outer boundary, it's set to 2.
So it's like they're saying, okay, within this band, within this donut, the critical values are behaving in a way that might be conducive to forming baby Mandelbrot sets.
Exactly.
Okay.
Now, the other 2 curves, which form the sides of the donut, are a little more complicated.
Okay.
They're what Boyd and Hoeppner call ray-like boundaries.
Ray-like.
Yeah. And these are determined by setting the critical values equal to complex numbers with specific arguments.
Okay, can you remind me what argument means in this context? It's been a while.
Oh, sure, yeah.
A little rusty.
So, in the complex plane, every number can be represented by its distance from the origin, that's the modulus, and its angle from the positive real axis, and that angle is the argument.
Right.
So by fixing the argument of the critical values, they're basically controlling the direction in which those critical values are allowed to move as the parameter A changes.
Okay, so it's like they're creating a path for the critical values to follow.
Exactly.
Okay.
And these ray-like boundaries are defined by setting the critical values equal to complex numbers with arguments equal to the argument of the fixed critical point plus or minus 2n.
Okay, so they're really carefully controlling how those critical values are allowed to move.
Yeah, it's all very carefully choreographed.
And this careful control, it's all part of their proof, right?
It is.
This movement of the critical values.
Yeah.
Oh.
So by defining these boundaries so precisely, they ensure that as A moves around this WCR region, the corresponding critical value winds around another region called VC. But crucially, it never intersects another important region called UA.
Okay, so it's like they're guiding this critical value along a very specific path.
Exactly.
Making sure it stays within certain bounds and avoids certain areas.
Right.
But why is it so important that it avoids that UA region?
Well, to prove that a function is polynomial-like, which is what they need to do, one of the key requirements is that the mapping between the smaller region UAK and the larger region UAK is
Meaning that points near the boundary of the smaller region get mapped to points near the boundary of the larger one.
Exactly.
Yeah.
And by ensuring that that critical value avoids UA, they guarantee that the mapping is indeed proper.
Oh, I see. So it all ties back to that concept of a proper mapping.
Yeah, it all comes together.
Okay.
Now, remember how we talked about those special A values, A2?
Yeah, where one of the critical values gets mapped onto itself.
Exactly. So for those special parameter values, the UA region is contained within the larger UA region.
All right. And that's a crucial condition for applying Dewey and Hubbard's theorem.
It is.
Which ultimately links those polynomial-like maps to the existence of baby Mandelbrot sets.
Yeah, it's all connected.
Okay.
But showing that a small region is contained within a larger region seems pretty straightforward, right?
Yeah, like just basic geometry.
You would think so.
Why did they need such intricate arguments to prove it in this case?
Well, it's not as simple as it sounds.
Oh, okay.
Because we're dealing with regions in the complex plane.
Right.
And the shapes and positions of these regions are determined by those parameters A and C.
Okay.
And their influence on the critical values.
Okay, so the complexity comes from how A and C actually control the shapes of these regions.
Exactly.
And the movement of those critical values.
Right. Yeah. So to prove that UA is contained within UA for those special A values, they used a really clever combination of geometric arguments. First, they established that UAK is always contained within that elliptical region E.
Right. The ellipse whose foci are the critical values.
Right.
Okay, so they're using the geometry of the ellipse to constrain the possible locations of that smaller region.
Precisely.
Okay.
And to do this, they analyzed the sum of the distances from any point in UAK to the two foci of the ellipse, B plus and B.
Okay.
And by showing that this sum is always less than a certain value, they could definitively prove that UAA must lie within the ellipse.
Okay, I'm seeing the logic here, but UA is only half of the ellipse, right?
Right.
So how do they go from showing containment within the entire ellipse to just that half?
Well, that's where their careful analysis of the boundaries of WCJ comes back in.
Okay.
Remember how they define those boundaries to ensure that the critical values never intersect UAK?
Yeah.
Well, they also carefully chose those boundaries so that the critical values would never cross the minor axis of the ellipse.
Ah, so they've essentially sectioned off half of the ellipse.
Exactly.
And made sure that UA stays within that designated area.
Precisely.
Okay.
And since UA is defined as half of the ellipse, they've now shown that UA is fully contained within UA.
Wow, so it's like they've choreographed the movements of these critical values to create the precise conditions needed for that containment.
It's really quite elegant.
It is.
And with this containment established, they've satisfied all the requirements of Doody and Hubbard's theorem.
Okay.
They've shown that their function, when restricted to that smaller region, behaves like a simpler quadratic polynomial.
Right.
And as A moves around the boundary of WCJ, the critical value winds once around the critical point, all while staying within that larger region.
So they've basically followed a mathematical recipe to prove that these baby Mandelbrot sets exist.
That's a great way to put it.
Okay.
Now, in the last part of our deep dive, we're going to shift gears a bit and talk about another fascinating discovery from their paper. These spines that emerge in the boundedness locus when they consider a specific relationship between A and C.
Yeah, those spines, I'm really curious about them.
They're really quite interesting.
Okay, let's hear all about them.
Okay, so those spines you were talking about.
Right, the spines.
Let's dive into those.
Okay, so these spines, they're denoted by sane, and they show up in the boundedness locus when we look at these slices of the parameter plane where C is related to A by the equation C equals T.
So we're fixing a relationship between A and C, and then seeing what happens to the boundedness locus.
Yeah, exactly. And in these slices, something really cool happens.
Okay.
The boundedness locus, instead of just being this blob of points, it actually clings to a curve.
Oh, wow.
And this curve, Saint, it acts as a kind of skeleton for the boundedness locus. It guides its shape.
So the spine is like a framework around which the boundedness locus takes shape.
Exactly. It's like a backbone.
Okay.
And what's even cooler is that they use the escape radius. Remember that boundary we talked about? Yes. To prove that the boundedness locus in these slices has to stay close to the spine.
So it's like the spine has this pull on the boundedness locus.
Yeah, like a gravitational pull.
Okay.
Keeping it from straying too far.
That's really interesting. How do they actually define these spines mathematically?
Well, remember how in the previous sections we were looking at those special A values where a critical value gets mapped onto itself?
Yeah, the IJ values.
Right. So in these diagonal slices, they shift their focus a bit.
Okay.
They start by looking at the Julius sets for these slices.
Okay. And remind me again what Julius sets are.
Sure. So each point in the Mandelbrot set corresponds to a particular Julius set.
Right.
And these Julius sets, they're those intricate fractal shapes that are kind of related to the Mandelbrot set.
Right. Okay. Got it.
So in these diagonal slices where C day, the Julius sets for the parameter values within the boundedness locus, they tend to cluster near the unit circle in the complex plane.
And this clustering behavior, it implies that any bounded critical orbits must also be close to the unit circle.
Right, because if the Julius sets are hanging out near the unit circle and the critical orbits are bounded, then they must also be in that same neighborhood.
Exactly. So to define the spine, they look for the values of A, where the modulus of the critical values, tana tonto, is equal to 1.
So they're finding the A values where the critical values lie right on the unit circle?
Exactly. And those A values, they make up the points of the spine.
Wow. So they're essentially pinpointing those parameter values where the critical values hit that sweet spot on the unit circle.
Yeah, that's a great way to put it.
And those form the spine.
Mm-hmm.
Okay, that's pretty cool.
And what's even more interesting is that the shape of the spine can actually change.
Really?
Depending on the value of t.
Oh, wow. So changing that one parameter t, which controls the relationship between A and C,
right,
can actually change the shape of this skeletal structure.
Yeah, it's like morphing the spine.
That's amazing.
Yeah, so for values of Tate greater than or equal to 1, the spine is a nice, smooth, connected curve.
Okay.
But for values of Tate less than 1, it splits into 2 separate curves.
It's like the spine is undergoing a transformation.
Yeah.
As we tweak that t parameter.
Exactly.
It makes you wonder what other kinds of surprises might be hidden in these mathematical structures.
Oh, I'm sure there are many more.
Yeah.
That's what makes complex dynamics so fascinating.
Right. There's always something new to discover.
Always.
So to recap, these spines appear in those slices of the parameter plane where she stayed Tay.
Right.
They're defined by the A values where the critical values are on the unit circle.
Mm-hmm.
And they act as a skeletal structure for the boundedness locus.
Exactly.
And Boyd and Hoeppner proved that the boundedness locus has to stay close to this spine.
Right, because of that escape radius concept.
Right, so it's like the spine is this safe haven from the chaos of infinity.
Yeah, I like that.
But they also mentioned some open questions in their paper.
They did.
What are some of the big unanswered questions?
Well, one of the big ones is whether we can actually find the centers of these baby Mandelbrot sets in these diagonal slices.
Okay.
Remember how in the earlier sections they were able to pinpoint those AJ values?
Yeah, which mark the centers of the baby Mandelbrot sets.
Exactly, but finding those centers in these diagonal slices, it's a lot harder.
Oh, why is that?
Well, that relationship between A and C,
okay,
it just makes the calculations much more challenging.
Right.
And they suggest that maybe looking more closely at this equation, Wn1g, 2 into 1 t2 is 0,
okay,
might give us some clues.
So it's like they've given us a map, but we still need to figure out how to read it.
Yeah, the treasure hunt continues.
Exactly. And what about what happens to the boundedness locus and the spine as n gets larger?
Right, that's another big question.
All of the results were sufficiently large, but what happens is we let n grow.
Yeah, that's something we don't know yet.
Does the boundedness locus become even more tightly bound to the spine?
Maybe.
Does the spine itself change?
It's possible.
These are questions for future mathematicians to explore.
Exactly, building on the work of Boyd and Hoeppner.
This has been such a fascinating journey.
It has.
We've explored these baby Mandelbrot sets, these polynomial-like maps, and even these amazing spines.
That's all thanks to the beauty of mathematics.
It is. It's amazing what we can discover with mathematical reasoning.
Absolutely.
And to our listeners, I hope this deep dive has inspired you to explore the world of math.
Yeah, keep asking questions.
There's so much more out there to discover.
Definitely.
Until next time, keep exploring. Welcome back, math enthusiasts, to another deep dive. Today we're going to journey into the captivating world of fractals. Specifically, we're going to be looking at baby Mandelbrot sets.
Oh, those are fascinating, aren't they?
Yeah, and the way they show up within Generalized McMullen Maps.
Absolutely, a really rich area of study.
Yeah, and you know, our listeners are no strangers to complex dynamics.
Definitely a knowledgeable audience.
So we're going deep today. We're going to be dissecting our source material. We'll be going step by step, walking you through the proofs and theorems that reveal these miniature Mandelbrot sets.
Sounds like a plan. It's always a pleasure to delve into the intricacies of these maps.
Yeah, absolutely. And we're going to be exploring two main avenues, right?
Right.
The first is what happens when we hold a parameter C constant. And then we're going to look at those intriguing diagonal slices where C is directly proportional to A.
Right. Those offer unique insights.
For sure. Before we get lost in the details, though, let's take a step back and make sure we're all on the same page. Can you remind us what generalized McMullen maps are and why they're so relevant to our discussion of baby Mandelbrot sets?
Certainly. Generalized McMullen maps are a family of complex rational functions. They're defined by the formula R sub AC sub Z IC sub Z equals sub plus A sub plus C.
Okay.
And in that formula, n is an integer. It has to be greater than or equal to 3.
Okay.
Z is our complex variable.
Okay.
And A and C, well, those are complex parameters.
Right, so those parameters, A and C, they seem to be pretty important players in this whole baby Mandelbrot set story.
They're absolutely critical. They hold the key to unlocking where those hidden baby Mandelbrot sets appear.
So by tweaking those parameters, we can basically navigate through the parameter space and see how the map's behavior changes.
Exactly. And in doing so, we can pinpoint those regions where the baby Mandelbrot sets emerge.
It's like exploring a hidden mathematical landscape.
That's a great way to put it.
But before we set off on our exploration, we should probably refresh our understanding of critical points and critical values. They seem to have a big impact on how these maps behave.
You're absolutely right. They're crucial. A critical point, remember, is where the derivative of the function vanishes or becomes undefined.
Okay.
And the critical value, well, that's simply the image of a critical point under the map.
Right. Those points are like signposts in our mathematical terrain, guiding us towards those areas of stability and chaos.
Precisely. And in the case of generalized McMullen maps, those critical points and values have some really intriguing properties.
Oh, like what? Fill me in.
Well, for one, these maps have 2n critical points.
Wow, so the number of critical points increases as n gets larger.
Exactly. But here's the really fascinating part. They only have 2 critical values.
Hold on. 2n critical points, but only 2 critical values. That seems counterintuitive. How's that possible?
It might seem surprising, but that's one of the unique characteristics of these maps.
So despite those 2n critical points being scattered across the complex plane, they all converge onto just 2 points when we apply the map.
Precisely. And those 2 critical values, they're given by Vivero plus up plus 2 plus 2 and vers up sub plus 2 oro.
So those 2 critical values, vers up plus sup and vers up sup, they're like the central figures in this whole mathematical drama.
Exactly. And their fate determines the overall plot. By analyzing their orbits, we can determine whether those orbits stay bounded or escape off to infinity.
Right, that distinction between bounded and unbounded orbits is key to identifying both the Mandelbrot set and its baby counterparts.
Precisely. It's like those critical values are tracing the outlines of these miniature fractal worlds.
Okay, so we've got our maps. We understand those critical points and values. Now, how do we actually visualize those boundedness regions and those baby Mandelbrot sets? I mean, we're dealing with complex numbers and iterated maps. It's not exactly something you can easily sketch on a piece of paper.
You're right. It's not easy to visualize directly. But that's where computers come in. We use algorithms that color code the parameter space based on what those critical orbits do.
So it's like creating a heat map of the parameter space.
Yeah.
The colors reveal those areas where the critical orbits remain bounded.
Exactly. And those colorful visualizations, they're not just pretty pictures. They provide valuable insights into the structure of the parameter space and guide our mathematical exploration.
It's like having a map to navigate those fractal landscapes.
Absolutely. They help us make conjectures about where those baby Mandelbrot sets might be hiding and what properties they might have.
It seems like we're well equipped to start our search for those baby Mandelbrot sets. But before we do, can we take a slight detour and talk about polynomial-like maps? I remember seeing that term in our source material, but I'm not quite sure how it fits into all of this.
Excellent point. Polynomial-like maps are essential because they bridge the gap between generalized McMullen maps and the well-studied theory of quadratic polynomials.
Okay, I'm listening.
You see, quadratic polynomials are the foundation of the classic Mandelbrot set. And it turns out that certain regions within the parameter space of those generalized McMullen maps, well, they act just like quadratic polynomials.
Interesting.
And that's where a crucial theorem comes in. Doody and Hubbard's theorem. It tells us that if a family of maps behaves like quadratic polynomials in certain regions, then we're guaranteed to find miniature copies of the Mandelbrot set within those regions.
So it's like those baby Mandelbrot sets are hiding in plain sight, disguised within those regions that mimic the behavior of quadratic polynomials.
Exactly. And Doody and Hubbard's theorem provides the tools we need to unmask them.
It sounds like a powerful tool. Can we delve a little deeper into those polynomial-like mappings and how they connect to our generalized McMullen maps?
Absolutely. The theorem focuses on mappings that are called polynomial-like. A mapping FUU is considered polynomial-like of degree D. If U and U are open subsets of the complex plane, U is relatively compact in U, and F is a proper holomorphic mapping of degree D.
Okay, let's break that down. We're dealing with two sets, U and U, with U nestled inside U. What does it mean for U to be relatively compact in U?
It essentially means that the closure of U is a compact subset of U. In simpler terms, U is snugly contained within U, and there's some breathing room between their boundaries.
Okay, so we're creating a controlled environment within U. Huh. What about that proper holomorphic mapping part? What does that entail?
A proper holomorphic mapping ensures that the map behaves nicely near the boundary of U. In technical terms, it means the inverse image of any compact set in U under the map F is also compact in U. This property is crucial for connecting the dynamics within U to the dynamics of a polynomial.
I see. We're setting the stage to make sure our map behaves predictably. Now, what about the degree of the map? You mentioned it earlier. Why is that important?
The degree of a polynomial-like mapping tells us how many times a point in U is covered by points in U under the map. Think of it like shining a light from a point in U onto U. The degree tells you how many shadows are cast in U.
Ah, so the degree is like a measure of complexity. And for those regions where the generalized McMullen map acts like a quadratic polynomial, we'd expect the degree to be 2, right?
Exactly. Now, Doty and Hubbard's theorem comes into play. It states that if we have a family of polynomial-like mappings, all of degree 2, and parameterized by a complex variable, then under certain conditions, this family will contain a homeomorphic copy of the Mandelbrot set.
Wait, homeomorphic copy, what exactly does that mean?
A homeomorphic copy is like taking a rubber sheet shaped like the classic Mandelbrot set. You can stretch and bend it, but can't tear it or glue any parts together. A homeomorphic copy is any shape you can make by doing that. It might look different, but it has the same basic topological properties as the original Mandelbrot set.
So even though the baby Mandelbrot set might appear distorted or stretched compared to the classic Mandelbrot set, it still shares that same fundamental structure and connectedness.
Precisely. And that's what makes Doty and Hubbard's theorem so powerful. It assures us that those baby Mandelbrot sets, even if they're a bit deformed, are true replicas of the classic Mandelbrot set in a topological sense.
Okay, this is all really fascinating, but we still haven't talked about those specific conditions that guarantee the existence of those baby Mandelbrot sets. What are they, and how do they apply to our generalized McMullen maps?
Right, let's get into those. The first step is connecting our generalized McMullen map to those polynomial-like mappings of degree 2. We need to pinpoint those special sets U and U in the complex plane where the map acts like a quadratic polynomial. Remember those sets, U sub a sub?
Yeah, you mentioned them earlier. Those were defined as polar rectangles in the complex plane, right?
Exactly. They play a crucial role in defining those regions. Remember, the generalized McMullen maps have the form R sub dn, 6 dub z equals z plus a, z plus c. Now, when z is large, the sub-terms dominate this expression. This means that far from the origin, the map behaves similarly to sub, which simplifies to 1. This gives us a hint about how to define those U sub subsets. We essentially want to choose regions where the map behaves like a power of z, eventually leading to that degree 2 behavior we need.
So we define those sets U sub k sub as specific polar rectangles in the complex plane to make sure those conditions for polynomial-like mappings are satisfied.
Precisely. And their definition involves our parameters a, n, and an index k that goes from 0 to 2 and 1. The exact formula is U sub k sub ziz a sub 1 sub ziz bidgies a plus 2k 2.210.
So we're basically defining a ring-shaped region centered at the origin, and it's sliced into 2 M pieces, each piece representing a different U sub x sub.
You got it. The first part of the formula, a sup 1 sub 2 z2, defines the ring. The inner radius depends on the nth root of the modulus of a divided by 2, and the outer radius is fixed at 2.
So the size of this ring changes with both a and n. If a gets larger, the ring grows, and if n increases, the ring shrinks.
Precisely. The second part, args plus 2k tuned to n, further restricts the values of z within this ring. Remember, a is the argument, or angle, of the complex parameter a. This condition essentially divides our ring into 2 equal-sized pieces, each centered at a different angle determined by k.
So each U sub x sub is like a slice of pie from that ring-shaped region. We have 2 of them. But how do these polar rectangles connect to the idea of polynomial-like mappings?
The key lies in how those U sub x sub are transformed under our generalized McMullen map, VLU E self-say sub. Each U sub sub maps onto a specific region, which we call either U sub plus sub sub or U sub sub, depending on whether K is even or odd.
Wait, so we have two n-polar rectangles, but they all map onto just two possible images.
That's right. And the reason goes back to the fact that all two critical points of R sub and A sub end up at just two critical values, versub plus sub and versub sub.
Ah, I see the connection now. Those critical values are pulling the strings, influencing the overall dynamics. But what do these U sub plus sub and U sub sub look like? Are they polar rectangles too?
Not quite. They both turn out to be halves of a special ellipse. This ellipse, let's call it E, is centered at the parameter C from our map and rotated counterclockwise by an angle of sub.
So both A and C are influencing the shape and orientation of this ellipse. What about the foci of this ellipse? Are they special in any way?
Absolutely. The foci of this ellipse are located precisely at the critical values of our map, versub plus sub and versub sub.
Wow, everything is interconnected. The critical values determine the foci of the ellipse, which in turn is the image of those carefully crafted polar rectangles.
You've got it. And Proposition 2.4 in our source material describes this mapping in detail. For even K, the image of U sub is U sub plus sub, one half of the ellipse E, including the minor axis and the critical value versub plus sub. For odd K, the image is U sub, the other half of the ellipse, also including the minor axis and V sub.
So those polar rectangles with even K values end up on one side of the ellipse, and those with odd K values go to the other side. I also noticed that Proposition 3.4 mentions that this mapping is 2 to 1.
Excellent observation. That means that for every point in U sub plus sub or U sub sub, there are 2 points in the original polar rectangle U sub that map to it.
So we have a 2 to 1 correspondence. It seems like we're building quite a complex and interconnected mathematical structure here.
We are, and the next step is to ensure that those sets, U sub and their images, meet the requirements for polynomial-like behavior.
Okay, remind me what those requirements are again.
One of them is that U sub needs to be relatively compact in U.
Right, we need that breathing room between the sets.
Exactly. In our situation, that translates to showing that U sub is relatively compact within its image, either U sub plus sub or U sub sub. And that's where lemma 3.5 comes in.
Okay, what does lemma 3.5 tell us?
It provides specific conditions under which we can be sure about that relative compactness.
So those conditions would bring us closer to fulfilling the criteria for those polynomial-like mappings, right?
Exactly. Lemma 3.5 states that if the modulus of C is at least 6 and n is large enough to satisfy the inequality 4C plus 8 at 2 sub piece plus 1 sub, then each U sub is relatively compact in its corresponding image, either U sub plus sub or U sub sub.
So we have some constraints on C, and the modulus of C has to be big enough and n needs to grow accordingly.
Precisely. And this makes intuitive sense, because as those values increase, the dynamics of the map get more complex, making those miniature Mandelbrot sets more likely to appear.
So by choosing our C and n carefully, we're creating an environment where those baby Mandelbrot sets can flourish.
That's one way to look at it.
But we still need to prove that the map, when restricted to U sub, actually behaves like a quadratic polynomial. Right? That's a key condition for Dewey and Hubbard's theorem.
Absolutely, that's the next hurdle. We need to demonstrate that the map, when zoomed in on those specific regions defined by U sub, essentially acts like a quadratic polynomial.
So how do we go about doing that?
Well, we turn to theorems 4.4 and 4.9 from our source material.
What do those theorems say?
They give us a set of very specific conditions. If those conditions are met, we can be sure that restricting R sub, high C sub to U sub, will make it behave just like a quadratic polynomial.
Okay, so we have a way to mathematically zoom in and confirm the quadratic nature of the map within those regions. What are those specific conditions?
The conditions involve carefully controlling the parameters A, C, and N.
How so?
We need to make sure that the images of U sub, those elliptical regions, U sub plus sub and U sub sub, are sufficiently far apart from each other. And we need to ensure that their boundaries don't intersect in a way that would disrupt the polynomial-like behavior we're looking for.
I see. It's all about setting up the right conditions for the map to reveal its quadratic nature.
Precisely.
So we've chosen suitable parameters, we've defined those special regions, U sub, and we've used theorems to confirm their quadratic nature. It seems like we're on the right track. What's the final piece of the puzzle?
You're absolutely right. The last step is that elegant winding number argument.
Right. I remember you mentioning that earlier. It's about analyzing how many times the image of the boundary of U sub wraps around one of those critical values, either versa plus sub or versa sub.
Exactly. We need to demonstrate that this winding number is indeed 2, which would confirm that the map is acting like a quadratic polynomial in those regions.
Right. The winding number serves as a kind of mathematical fingerprint. But how do we actually calculate it? It seems like a pretty intricate task.
It can be, but thankfully, complex analysis provides us with some handy tools. One of them is the argument principle, which links the winding number to the number of zeros and poles of a function within a given region.
I vaguely remember the argument principle from complex analysis.
Well, by carefully selecting a contour of integration that encloses u sub, and applying the argument principle to our generalized McMullen map, we can show that the winding number is indeed 2.
And that would satisfy the final requirement of Duadian-Hubbard's theorem.
Exactly.
We've come a long way. We started with those generalized McMullen maps. We explore the significance of those critical points and values.
Yes.
We define those special polar rectangles, u sub, and confirm that within those regions, the map behaves just like a quadratic polynomial.
That's right.
And finally, we use the argument principle to verify that the winding number is 2. It's remarkable how all these pieces fit together so beautifully to prove the existence of those baby Mandelbrot sets.
It truly is a testament to the elegance and power of complex dynamics.
Absolutely. Now that we have this solid foundation, I'm excited to dive into those specific scenarios where those baby Mandelbrot sets make their grand appearance.
Me too. Let's explore. So now we're going to explore those scenarios where those baby Mandelbrot sets actually reveal themselves.
Yeah, let's do it. Where do we start?
Let's hold the parameter c constant,
okay,
and we'll see what happens in the A-plane as we let it vary.
So it's like taking a slice through that parameter space.
Yeah, I see.
We're holding a c steady and letting it roam free. What kinds of patterns do we see when we do that?
Well, in this scenario, we're really interested in what's called the boundedness locus in the A-plane. It's denoted by m sub, r sub and a sub. This set includes all the A values, where at least one of the critical orbits of R sub A sub stays bounded.
Okay, and remember, those critical orbits are determined by the critical values versa plus 2 Liska and versa within C diesa.
Right, those critical values are our guides.
So by looking at what happens to versa plus sub and versa sub as we change A, we can map out those stable regions in the A-plane.
Precisely. And those stable regions, those are where the critical orbits stay bounded. And guess what? Those are the very places where those baby Mandelbrot sets hang out.
Ah, so it's like those critical values are leading us straight to those hidden fractal treasures.
Exactly. Now, the specific shapes and arrangements of those baby Mandelbrot sets within the A-plane, they depend on the value of C.
So how does choosing different C values affect how those baby Mandelbrot sets look? Can you give me some examples?
Sure. If you pick a C value with a smaller modulus, those baby Mandelbrot sets might look a bit distorted or merged. They'll create these intricate patterns that are a bit different from the classic Mandelbrot shape.
So each baby Mandelbrot set has its own unique personality, shaped by the value of C.
That's a great way to think about it. Now, as we make the modulus of C larger, something interesting happens, especially when it becomes greater than 1.
What happens?
We start to see these distinct primary baby Mandelbrot sets appearing in the A-plane. And the number of these primary baby Mandelbrot sets is directly determined by the parameter n.
So as n increases, not only does the complexity of the map go up, but so does the number of those baby Mandelbrot sets.
Exactly. And each of these primary baby Mandelbrot sets is associated with a fixed point of a particular equation.
What equation is that?
The equation is 1 sub n, 1 sub 2, 2 sub 2, and 1 sub t is 0, where t equals a.
You know, that equation looks familiar. Didn't we see something similar when we were talking about those fixed critical points in the context of the diagonal slices?
You've got a sharp eye. Yes, we did. Those fixed critical points, where the map sends a critical point back onto itself, are closely tied to the existence of baby Mandelbrot sets. And when we keep substant, those fixed critical points become the anchor points for those primary baby Mandelbrot sets in the A-plane.
Okay, I'm starting to see those connections. We've got two in primary baby Mandelbrot sets, each linked to a fixed critical point. How do we go about proving that these baby Mandelbrot sets actually exist?
Well, it's not a simple proof. But fortunately, we have a powerful theorem to guide us. It's main theorem 1 from our source material.
What does that theorem tell us?
It tells us that under certain conditions, we're guaranteed to find those primary baby Mandelbrot sets, specifically if the modulus of C is greater than or equal to 6, and n is large enough to satisfy 4c plus 8, 2 sub n plus 1 sub, then there will be in primary homeomorphic copies of the Mandelbrot set within the boundedness locus m sub a sub in the A-plane.
Wow, so if we meet those criteria for C and N, we know those baby Mandelbrot sets have to be there. But how do we actually prove this theorem? What's the strategy?
It involves a clever combination of ideas from complex dynamics and topology.
Okay.
We start by remembering lemma 3.5, which, if you recall, established that under the right conditions on C and N, each of those polar rectangles, U sub daga, is relatively compact in its corresponding image under the map, whether it's U sub plus sub sub or U sub sub sub.
Right. That lemma gave us those well-behaved regions where we can study how the map behaves. What's next?
Next, we have to show that the map, when restricted to each U sub, behaves just like a quadratic polynomial. Remember those conditions for polynomial-like mappings?
Right.
We need to make sure the map meets all those criteria.
So we need to prove that when we zoom in on those specific regions defined by U sub, the map is essentially putting on a quadratic polynomial disguise.
Exactly.
How do we do that?
That's where theorems 4.4 and 4.9 from our source material come in. These theorems provide a specific set of conditions that, when satisfied, guarantee that the restriction of suba phi sub to u sub acts just like a quadratic polynomial.
So those theorems are like our mathematical magnifying glasses. We can use them to zoom in and confirm the quadratic nature of those regions. What are those conditions exactly?
They involve making sure the images of u sub, those elliptical regions, U sub plus sub and U sub, are sufficiently far apart from each other, and their boundaries don't intersect in a way that would mess up the polynomial-like behavior we're after.
It's all about setting up those precise conditions so the map can show off its quadratic side.
You got it.
Okay, so we've carefully chosen our C and N, defined those special regions, U sub, and use those theorems to confirm they have that quadratic nature. Seems like we're hitting all the points required by Dewey and Hubbard's theorem. What's the last step?
You're right, we're almost there. The last step is that winding number argument. We need to analyze how many times the image of the boundary of U sub wraps around one of the critical values, versup plus sup or versup, and we have to show that this winding number is 2.
Right, that winding number is like a mathematical fingerprint revealing the degree of the map. But how do we actually calculate it?
We can use a technique called the argument principle. It relates the winding number to the number of zeros and poles of a function in a particular region.
Okay.
By choosing the right contour of integration that encloses U sub and applying the argument principle to our generalized McMullen map, we can prove that the winding number is indeed 2.
And that would check off the final requirement of Dewey and Hubbard's theorem. We've successfully put all the pieces together.
It's pretty amazing how all those concepts come together.
We started with choosing the right values for C and N. Then we defined those special polar rectangles, U sub. Then we used theorems to confirm their quadratic nature.
Right.
And finally, we brought in the argument principle to verify that winding number. It's like a mathematical symphony.
It really is. And it all leads to the beautiful conclusion that those n primary baby Mandelbrot sets exist.
It's incredible how much we can learn by carefully analyzing those maps and applying those powerful tools from complex analysis.
Absolutely. And now that we've explored the scenario where C is constant, I think it's time to move on to those intriguing diagonal slices.
Yeah, let's delve into those. I'm curious to see what happens when we let C be proportional to A.
Now we get to explore those diagonal slices where C is directly proportional to A.
Yeah, this is where things get even more interesting, right? We're linking those parameters together instead of keeping one fixed. How does that affect those baby Mandelbrot sets?
Well, these diagonal slices give us a unique perspective on the boundedness locus.
Okay.
It's in these slices that we encounter the idea of spines.
Spines? What are those?
They're these special curves in the parameter plane that act as guides for finding those baby Mandelbrot sets.
Okay, I'm intrigued. How are they defined?
For these generalized McMullen maps, where C equals ter ta, the spines, which are denoted as sub, are defined by a specific equation. Equation 3 in our source material tells us that the spines are the set of all complex numbers a that satisfy the condition ter ta equals 1. So for any a value on a spine, the modulus of either ta plus 2 eris or tira has to equal 1.
So those spines are basically the a values that keep those critical values, tegeturia, close to the unit circle. And we know those critical values are key to understanding how the map behaves.
Precisely. We're zeroing in on those regions where the map's behavior is the most sensitive, and that's where those baby Mandelbrot sets are most likely to be found.
It's like we're using those spines as a treasure map to lead us to those hidden mathematical gems.
That's a great way to put it.
So what do these spines look like? Are they straight lines, curves, or something else entirely?
Their shape depends on the value of teat. They can be these smooth, continuous curves winding through the parameter plane. But for certain values of teat, they might split into two separate branches, which makes for a much more intricate pattern.
I'm looking at figure 13 in our source material, and it's fascinating how those spines create a kind of framework for those baby Mandelbrot sets to emerge.
Exactly. But we still need to prove that the boundedness locus, those stable regions, actually stays close to those spines.
How do we do that?
That's where main theorem 2 enters the picture.
What does main theorem 2 say?
It states that for any positive number, epsilon, no matter how small, we can always find a large enough integer n such that the boundedness locus m sub pesata sub is completely contained within an epsilon neighborhood of the spine, sub.
So the larger we make n, the closer the boundedness locus gets to those spines.
Precisely. This theorem shows a strong link between those visually striking spines and where we can find those baby Mandelbrot sets.
It's like those spines are magnets and the boundedness locus can't resist their pull.
Exactly.
So how do we prove this theorem?
It involves a few steps. First, we recall lemma 5.2, which gives us an annulus that contains the boundedness locus.
Right, that's like a safe zone for those critical orbits.
Exactly. Then we bring in corollary 2.4.
And what does that tell us?
It tells us that if an n is large enough, the filled Julia sets are contained within a small neighborhood of the unit circle. Now remember, the spines themselves are defined as those a values that keep those critical values close to the unit circle. And if those filled Julia sets are also near the unit circle, then it makes sense that the boundedness locus, which is all about those bounded orbits, would have to be close to the spine as well.
So it's all connected. Those spines, the filled Julia sets, and the critical values are all influencing each other.
Precisely. And the formal proof makes this intuition rigorous. It uses a proof by contradiction. We assume that there is some a value in the boundedness locus that's far from the spine. Then we show that this assumption leads to a contradiction, meaning such an a value can't exist.
So we essentially prove that the boundedness locus has to stay close to those spines.
That's right. And that wraps up the proof of main theorem 2, showing the tight relationship between those spines and where we find those baby Mandelbrot sets.
It's fascinating how we've used those concepts from complex analysis, topology, and geometry to reach this conclusion.
It really is. It shows the beauty and elegance of these mathematical tools.
We've come a long way on this deep dive. We've explored the world of baby Mandelbrot sets. We've looked at how they hide within those generalized McMullen maps.
Yes.
And we've uncovered the mathematical principles that govern their existence.
It's been quite a journey.
Indeed. We started with those fundamental definitions, carefully dissected those theorems, and used those powerful tools like the argument principle to really understand the intricate dynamics of these maps.
And we've seen those fascinating connections between seemingly abstract mathematical concepts and the visual beauty of those fractal structures.
Absolutely. It's a reminder that mathematics is not just about formulas and equations. It's about exploration, discovery, and the sheer joy of unraveling the mysteries of the universe. And for those of you eager to continue the exploration, there are always more layers to uncover, more connections to make, and more beautiful mathematical landscapes to explore. So keep that curiosity alive and those minds engaged. Welcome back to another deep dive. Today we'll be exploring fascinating mathematical terrain.
Oh, cool.
Specifically, baby Mandelbrot sets and spines.
Okay.
Within Generalized McMullen Maps.
Yeah.
You shared some excerpts from a paper with that exact title, and it looks like we're in for a real treat here.
Awesome.
Now, since you're a math whiz,
Oh, thanks.
We could skip the intro to fractals and dive right into the good stuff.
Sounds good. I'm always excited to see how these Mandelbrot-like structures pop up in different mathematical contexts.
It's amazing how those intricate patterns can emerge from seemingly simple equations.
Totally.
So just to set the stage a bit, we're dealing with generalized McMullen maps, which have the form R sub n a c of z equals z to the n plus a divided by z to the n plus c.
Right.
Where n is an integer greater than or equal to 3, and a and c are complex parameters.
Exactly. And just like with the classic Mandelbrot set, the focus here is on the boundedness locus, denoted m sub n of R sub n a c.
Right.
That's the set of parameter values AC, for which at least one critical orbit of our map remains bounded under iteration.
So instead of just varying C like we do in the classic Mandelbrot set, here we have two parameters to play with, A and C.
Exactly.
That opens up a whole new landscape of possibilities.
Absolutely. It's like exploring a two-dimensional parameter space.
Wow.
Instead of just a one-dimensional line.
Yeah.
And the paper dives into two main avenues within this space.
Okay.
First, it examines what happens when we fix C and let A vary.
So we're taking vertical slices through this AZ parameter plane.
Exactly.
And what did they find there?
What's fascinating is that under certain conditions on C and N, they discovered n baby Mandelbrot sets within those slices.
Wow.
Imagine miniature copies of the Mandelbrot set, each centered around a different point in the 8 plane.
That's mind-blowing.
Yeah.
So these baby Mandelbrot sets are like hidden gems tucked away within this larger structure.
Exactly.
And what about the second avenue of exploration?
The second part delves into slices.
Okay.
Where C is tied to A through a linear relationship. Specifically, C equals T.
Okay.
Where T is a fixed complex number.
Ah, so we're looking at diagonal cuts through the parameter space now.
Exactly.
And that's where the spines come in.
Right.
Okay.
The boundedness locus in these diagonal slices exhibits a fascinating behavior, organizing itself around a curve they call the spine, denoted S sub T.
Intriguing. But before we get to the spines, I'm curious about how they even visualized these boundedness loci in the first place. Remember, we're dealing with two critical orbits here, V plus and V minus. How do we represent that visually?
They used a clever color scheme to capture the dynamics of both critical orbits.
Okay.
Each critical orbit was assigned a distinct color.
Okay.
Then for every point in the parameter plane, they iterated the map and observed the behavior of each orbit.
Yeah.
If both orbits remained bounded, the point was colored black.
Okay, that makes sense. Black for boundedness, just like in the classic Mandelbrot set.
Exactly.
But what if one or both orbits escaped?
If one orbit escaped, they'd use its designated color, with the shade indicating how quickly it escaped. If both escaped, the final color of the point was an average of the two colors, reflecting the escape behavior of both orbits.
Ah, so those beautiful swirling colors we see in the images are like a visual fingerprint of the critical orbit's behavior.
Precisely.
Very cool.
Yeah.
Okay, so we have these images, but how did they actually go about identifying those baby Mandelbrot sets?
Yeah.
I know the concept of polynomial-like maps plays a key role here.
You're right.
Yeah.
The theoretical foundation for identifying these baby Mandelbrot sets comes from Dewey and Hubbard's work on polynomial-like maps.
Gotcha.
Essentially, a polynomial-like map that behaves very similarly to a polynomial on a certain region of the complex plane.
Right. So it's like saying, hey, even though our generalized McMullen map is more complicated than a simple quadratic polynomial, it acts almost exactly like one in this particular region.
Exactly. And the key is if we can find these regions where our map exhibits polynomial-like behavior, then we can apply Dewey and Hubbard's theory to prove the existence of a baby Mandelbrot set within that region.
I see. So it's like finding those hidden pockets of Mandelbrot-like dynamics within a more complex mathematical landscape.
Perfect analogy.
Right.
And the paper goes on to show that this containment occurs in different ways depending on the values of A, C, and N.
Okay.
To do this, they introduce specific polar rectangles in the complex plane and examine how they transform under the McMullen map.
Okay, let's dive into the details there.
Sure.
The paper mentions these polar rectangles denoted U sub A k prime.
Right.
And their images under the map denoted U sub A k.
Okay.
What's the significance of these regions?
These U sub A k prime are carefully constructed regions that depend on A and N, but importantly not on C initially. Their images, the U sub A k, do depend on C. And the key to identifying baby Mandelbrot sets lies in analyzing how these images transform as we vary the parameters.
So we're transforming these rectangles based on our McMullen map. Yeah. And what are we looking for in these transformations?
The crucial property we're after is containment.
Containment,
The paper aims to show that for specific parameter ranges, the original rectangle U sub A k prime is fully contained within its image, U sub A k.
And why is that containment so important?
Because that containment is one of the key criteria for establishing polynomial-like behavior. It means we found a region that's folding in on itself, just like a quadratic polynomial would, creating those self-similar patterns characteristic of Mandelbrot sets.
That makes sense. It's like the image of the rectangle swallowing the original rectangle whole.
Precisely.
Okay, so far so good. But then things start to get a bit more complex with the introduction of ellipses and escape radii. Can you walk us through those concepts?
Of course.
Okay.
Remember our two critical values, V plus and V minus. They define an important ellipse in the complex plane. This ellipse, denoted E, is centered at the parameter C and rotated by psi divided by 2, where psi is the argument of A.
So the critical values act as the foci of this ellipse.
Exactly. Now the paper shows that the image of our polar rectangle, U sub A k prime, can be understood geometrically as half of this ellipse. And that geometric understanding of how these rectangles transform within the ellipse is key to identifying potential Beatty-Mandelbrot sets.
I'm starting to see the connection between the geometry and the dynamics here. The ellipse provides a kind of visual boundary for the action of the McMullen map.
Exactly. And the escape radius adds another layer to this understanding. Lemma 3.5 in the paper establishes an escape radius as, for R sub n, A, C. Any orbit that ventures beyond this radius is guaranteed to escape to infinity.
So it's like a point of no return. Once an orbit crosses that radius, it's gone for good.
Precisely. And then using the involution symmetry of McMullen maps, which basically means they have a special kind of symmetry, under the transformation z goes to 1 over z, they find a corresponding neighborhood around the origin of radius t, where orbits also escape.
Interesting. So we have these two regions, one near zero and one far away, where the filled Julia set must be avoided.
Exactly. And that leaves us with an annulus denoted A of T, S, which must contain the filled Julia set. K of R sub N AC.
That's clever.
It's like they're closing in on the region where the truly interesting dynamics occur.
Okay, so we have this geometric setup with the ellipse and the escape radii. Now, how do they actually use these tools to pinpoint those baby Mandelbrot sets?
The paper then goes on to examine specific cases based on the values of C. The first case they tackle is when the modulus of C is small.
Okay, so let's start there. What happens when we constrain C to be small?
Well, when the modulus of C is less than T, that inner escape radius we talked about, and the modulus of A is less than or equal to 4. Proposition 4.1 tells us that all of the use of A, K prime lie within our ellipse E.
So they're all neatly contained within that elliptical boundary defined by the critical values. And then things get even more specific when C is real and positive for odd values of n. They prove that U sub A, n prime, the rectangle centered around the negative real axis, is contained within U sub negative A, which is the image of the rectangle centered around psi plus pi divided by n. Okay, hold on. Why is that significant?
That's a great question.
Yeah.
And this is where the magic starts to happen.
Okay.
Because that specific containment relationship means we've found a region where our McMullen map acts just like a quadratic polynomial.
Oh.
It satisfies all the conditions for polynomial-like behavior that we talked about earlier.
So that containment is the key that unlocks the door
Precisely.
to finding baby Mandelbrot sets.
Yes. And it leads to the identification of a baby Julia set.
Oh, cool.
Which is like a miniature version of the filled Julia set of a quadratic polynomial.
Wow, so we've actually found one of those miniature Julia sets. The building blocks of the baby Mandelbrot sets.
Exactly. And Theorem 4.4 makes it official.
Okay.
It states that for these specific parameters, a portion of the filled Julia set of R sub n, AC, is topologically conjugate to a quadratic Julia set.
Now, I vaguely remember topological conjugacy from my dynamical systems days.
Right.
Can you remind us what that means?
Of course.
Okay.
Essentially, it means that there's a homeomorphism, a continuous function with a continuous inverse that maps the dynamics of one system onto the other.
Okay.
So in this case, it means that the behavior of orbits in a portion of the filled Julia set of our McMullen map is essentially the same as the behavior of orbits in a quadratic Julia set, just viewed through a slightly distorted lens.
Oh, that's a helpful reminder.
Yeah.
So it's not an exact copy.
Right.
But it's structurally and dynamically equivalent to a quadratic Julia set.
And this finding sets the stage for the exploration of even more complex behavior as we vary the parameters further.
This is already so fascinating. We've explored those initial results for small c values.
Right.
Found our first baby Julia set. And even touched upon some deep concepts like topological conjugacy.
Exactly.
Where do we go from here?
Right.
What happens when C gets larger?
Things get even more interesting when we let C grow. Well, that's where we'll start to see those and baby Mandelbrot sets emerge in their full glory.
Okay.
But I think that's a perfect place to pause for now.
Agreed.
And let our listener digest all these intricate details.
We've covered a lot of ground.
Yes, we have.
And I'm sure our listeners eager to see what surprises await us in the realm of larger C values.
Absolutely.
Stay tuned.
All right. Welcome back. I'm excited to delve further into this intricate world of baby Mandelbrot sets.
Last time we explored those initial results for small c values, found our first baby Julia set, and even touched upon some deep concepts like topological conjugacy.
Yeah.
But I'm ready to see what happens when C starts to grow.
Yes.
The paper hints at even more fascinating discoveries.
You're in for a treat.
Okay.
As C gets larger, the dynamics become more complex, and those N baby Mandelbrot sets we mentioned earlier start to emerge.
Okay, so let's jump right in.
Okay.
The paper focuses on the case where the modulus of C is greater than or equal to 6.
Yes.
What's so special about that value?
That value is crucial.
Okay.
Because it ties into a specific condition for finding fixed critical points.
Okay.
Remember Lemma 2.5 from the paper?
Yeah, vaguely.
It states that for the modulus of C greater than 1, there are n distinct solutions to the equation C plus or minus 2 times the square root of A equals A to the 1 over 2n.
Right. I remember that lemma.
Yeah.
And those solutions represent parameter values where the critical points of our McMullen map are also fixed points.
Exactly. And those fixed critical points are the likely centers of our baby Mandelbrot sets.
Wow.
So to explore this further,
the
paper introduces these carefully defined regions in the A plane, denoted W sub C. Each of these regions is designed to contain one of those potential baby Mandelbrot sets, centered around a fixed critical point.
Interesting. So it's like they're drawing a circle around each potential baby Mandelbrot set.
Yeah.
Can you walk us through how these W sub CJ regions are constructed? They seem pretty intricate.
They are.
Yeah.
Each W sub CJ is bounded by 4 curves.
Okay.
2 of these curves, the inner and outer boundaries, are close to circles and are determined by setting the modulus of those critical value expressions we discussed. The modulus of C plus or minus 2 times the square root of it equal to 1/2 and 2. respectively.
Yeah. Okay, so those boundaries are like concentric rings around our potential baby Mandelbrot set, ensuring that the critical values stay within a certain range.
Exactly.
And then we have two more boundaries, sometimes called ray-like boundaries, which are actually arcs of parabolas. These are derived by setting those critical value expressions equal to x times e to the I times the quantity argument of w sub j, plus or minus pi divided by 2n, where x is a real number between 1/2 and 2.
Correct.
Whoa. Hold on, a lot is going on in that expression.
Yeah.
Can you unpack it for us?
Sure.
What's w sub j in this context?
Of course. Remember, each w sub c j is associated with a specific fixed critical point, which we can denote as a sub j.
Okay.
Now, w sub j represents the value of our McMullen map at that fixed critical point. In other words, w sub j equals r sub n, a sub jc of a sub j.
Okay, that makes sense.
Yeah.
So these ray boundaries, which are actually parabolic arcs, are essentially tracking how the argument of the critical value changes as we move around the boundary of w sub c.
Right.
They're ensuring that the critical value stays within a certain angular sector.
Precisely.
Okay.
And these boundaries are carefully chosen
to ensure that as the parameter a travels around the boundary of w sub c, j, the corresponding critical value winds once around a specific region in the dynamical plane, the plane where the function is being iterated.
So we're not just moving around in the A plane, we're also tracking how things are moving in the dynamical plane where the function is being iterated.
Absolutely. It's like a synchronized dance between the parameter space and the dynamical plane. And that connection is crucial because it allows us to apply Duty and Hubbard's theorem to prove the existence of baby Mandelbrot sets.
To prove that we have a baby Mandelbrot set, we need to show that as the parameter A traces a loop around a certain region, the corresponding critical value winds once around the critical point in the dynamical plane.
Exactly.
Okay.
So to get there, the paper first needs to establish
that our McMullen map, R sub n AC, is indeed polynomial-like on each of these W sub Cj regions.
And that means going back to those containment relationships between the U sub a k prime and their images. The U sub a k,
Again, establishing that containment is essential for proving polynomial-like behavior. The journey starts with lemma 4.12, which lays the groundwork by proving that for any A within any W sub C, JA, the disk of radius 2 centered at the origin is entirely contained within our ellipse, E.
Okay, so the ellipse acts as a kind of outer boundary of the action.
And since the U sub A, K prime are always inside that disk of radius 2, they're also contained within E.
So we've got the ellipse as our outer boundary. But what about the relationship between U sub A, K prime and its image, U sub A, K? That's the crucial containment we need for polynomial-like behavior.
That's where things get a bit more intricate. Lemma 4.13 focuses on how the argument of A changes as we move throughout W sub C, J. They prove that the argument of any critical point can change by no more than pi divided by 2n within this region.
Okay, I'm following so far. But why is that restriction on the argument of A so important?
It's important because it ensures that the angular difference between the critical point and its image, which is the critical value, stays within a certain bound.
So as the parameter moves around within W sub C, the critical point and its image are kind of moving together in a controlled way. Always staying relatively close to each other in terms of their angle.
Precisely. And lemma 4.14 builds on this by showing that U sub A, K prime, is always contained within a disk of radius 2 times the square root of the modulus of a chimera centered at the appropriate critical value.
I see. So we're using these circles around the critical values to make sure that U sub A, K, and Temeller prime doesn't stray too far from its image. U sub AK.
And because the critical values are constrained to lie close to the unit circle due to how we define the boundaries of W sub C. This containment within the disk.
Guaranteed, yeah.
That u sub a k prime never intersects the minor axis of our ellipse, E.
Okay, that's a clever bit of geometric reasoning.
Yeah.
So we're preventing u sub a k prime
yes.
from crossing over into the wrong half of the ellipse.
Exactly.
Which would break that crucial containment property we need for polynomial-like behavior.
You've got it.
Okay.
It's all about carefully controlling the geometry to ensure the dynamics behave the way we want them to.
Gotcha.
And all of this careful analysis leads to Proposition 4.15, which officially declares that R sub n, AC, is polynomial-like of degree 2 on each u sub a, k of j for all a within w sub cj.
That's a big step. It is. We've officially met the first 4 conditions of Duetty and Hubbard's theorem.
Yeah.
Which means we're on the verge of proving the existence of those baby Mandelbrot sets.
We're almost there.
Okay.
Now we just need to tackle that 5th and final condition. Showing that the critical value winds once around the critical point as the parameter A loops around the boundary of W sub g.
That's the last piece of the puzzle, right?
It is.
Okay.
And lemma 4.16 delivers that final piece.
Right.
It proves that as A traces the boundary of W sub C, J, the corresponding critical value, neatly winds once around the region U sub A, K minus U sub A, K prime, which means it also winds once around the critical point itself.
So we've got that crucial winding behavior.
We do.
It's like the critical value is doing a little dance.
A perfect analogy.
Around the critical point as the parameter moves.
And with that final condition met, we arrive at Theorem 1 in all its glory. It states that for the modulus of C greater than or equal to 6 and n large enough, there are at least n baby Mandelbrot sets nestled within those W sub CJ regions in the A-plane of our McMullen map.
Wow, what a journey.
I know, it's pretty amazing.
From those seemingly simple equations to these intricate fractal landscapes, it's truly mind-blowing.
It is.
We've uncovered those hidden baby Mandelbrot sets within the parameter space of Generalized McMullen Maps.
We have.
But wait, there's more, right?
There is.
The paper also explores those diagonal slices where C is tied to A through the relationship C equals T. That's where those intriguing spines come into play.
You're exactly right.
Okay.
And exploring those spines will reveal another layer of complexity and beauty within this mathematical world.
I'm ready for more. Let's dive into the world of spines.
Welcome back. We've been on quite a mathematical adventure.
It has been quite a journey.
Exploring these intricate baby Mandelbrot sets hidden within the parameter space of Generalized McMullen Maps.
We've explored those initial results for small C values. Found our first baby Julia set. And then ventured into the realm of larger C values where those n baby Mandelbrot sets reside within those carefully constructed Win sub J sub regions. But now I'm excited to delve into the second part of the paper. Those intriguing spines that emerge when we consider diagonal slices through the parameter space where C is tied to A through the relationship C equals T.
Ah, yes, the spines.
Yes.
They offer a different perspective on the boundedness locus and reveal a fascinating connection between the geometry of these slices and the dynamics of the McMullen maps.
Okay, so let's dive right in.
All right.
What exactly is a spine in this context? And how does it relate to the boundedness locus?
In these diagonal slices where C equals T,
the boundedness locus takes on a different kind of structure. Instead of being contained within those Win sub J sub regions we discussed earlier, it tends to cluster around a specific curve called the spine, denoted by S sub T.
Gotcha.
Think of the spine as the backbone of the boundedness locus in these slices.
I like that analogy. The spine provides the structure around which all the interesting dynamics occur.
Exactly.
But how do we actually find this spine? What does it look like mathematically?
Equation 3 in the paper provides the formula for the spine. It states that S sub T is the set of all A values that satisfy the equation modulus of T plus or minus 2 times the square root of A equals 1.
Okay, let's break that down. We have T, which is just C, based on our diagonal slice condition.
Exactly.
Then we have plus or minus 2 times the square root of A,
Which reminds me of those critical value expressions we saw earlier.
Exactly.
And the whole thing is set equal to 1.
Right.
What's the significance of that?
You've hit the nail on the head.
Okay.
That equation is essentially defining a set of A values where the critical values, t plus or minus 2 times the square root of a, lie on the unit circle in the complex plane.
Ah, I see.
Yeah.
So the spine is like a curve that traces out all the points in the A plane.
Yes.
Where those critical values are tethered to the unit circle.
A great way to visualize it.
Thanks.
And the shape of the spine can vary dramatically depending on the value of t. That complex slope in our C equals t relationship.
Right.
When the modulus of t is less than 1, 2, the spine bifurcates.
Right.
Creating those 2 separate branches you mentioned.
Yeah, I'm looking at figure 13 in the paper, which shows several examples of spines for different values of t.
Right.
Some of them are simple loops.
While others are more intricate.
Yes.
Even splitting into 2 disconnected curves.
Exactly.
It's fascinating how a single parameter, t, can have such a dramatic impact on the shape of the spine.
It is.
But how do we know
that
the boundedness locus actually stays close to this spine?
That's a great point.
Yeah.
Just because the critical values are on the unit circle doesn't guarantee that.
Right.
But fear not, the paper addresses this through Theorem 2.
Right.
Which provides the rigorous proof we need.
Right.
It states that for sufficiently large n, the boundedness locus, m sub n, of r sub n, a, t, lies within an epsilon neighborhood of the spine s sub t.
Okay, so they're essentially saying that as n increases, the boundedness locus gets squeezed tighter and tighter.
Precisely. And they achieve this by first containing m sub n of r sub n, a, within an annulus, a ring-shaped region.
Based on the modulus of ep.
I'm trying to picture this.
Yeah.
We have the spine sneaking through the A plane.
Right.
And then we have this ring, or annulus, that encloses it.
Right.
And the boundedness locus has to stay within that ring.
Exactly. Lemma 5.2 establishes that for large enough and the boundedness locus is trapped within that annulus.
Right, but we want to show that it's not just within the ring.
Yes.
It's actually hugging the spine in that ring.
That's where the proof of Theorem 2 gets really clever.
Okay.
They use what's called a covering argument.
Gotcha.
They take that annulus we established and remove an epsilon neighborhood of the spine from it.
Okay.
Then they show that for any point outside that epsilon neighborhood, any point that's not close to the spine, the critical values must lie outside the filled Julia set for sufficiently large n.
Ah, that makes sense.
Yeah.
They're essentially saying, look, if you're not close to the spine, your critical values are going to escape.
Right.
And you can't be part of the boundedness locus.
Right.
So the only points that can remain in the boundedness locus are those that are within that epsilon neighborhood of the spine.
Precisely.
Okay.
It's a powerful argument that establishes the spine as the true organizing principle for the boundedness locus in these diagonal slices.
This is all so fascinating.
Yeah.
But I have to admit, there's still one question lingering in my mind.
Okay.
We've explored these spines.
Right.
We've shown that the boundedness locus clings to them. But have we actually proven that baby Mandelbrot sets exist in these slices?
That's an astute observation. While the paper focuses primarily on establishing the location and behavior of the boundedness locus in relation to these spines, it doesn't definitively prove the existence of baby Mandelbrot sets in these diagonal slices.
So there's still more to explore. It's like the paper has given us a treasure map.
Yeah, that's a good analogy.
Pointing us toward these potentially hidden baby Mandelbrot sets.
Right.
But it's up to future explorers to actually unearth them.
Precisely.
Okay.
The authors acknowledge this in the future work section, suggesting that the next step would be to pinpoint the centers of those potential baby Mandelbrot sets within these slices, and then apply those polynomial-like mapping techniques we discussed earlier to rigorously prove their existence.
It's amazing how even a single research paper can open up so many new avenues for exploration.
It is.
This paper feels like a launch pad.
It does.
For so much more investigation.
Absolutely.
Well, I think we've done a phenomenal job unpacking this paper.
We have. It's been a great discussion.
We've delved into the fascinating world of baby Mandelbrot sets within the parameter space of generalized McMullen maps, exploring how these intricate fractal structures emerge and how their existence can be rigorously proven.
We have.
We've journeyed through the parameter plane.
It's been a true deep dive.
Examining vertical and diagonal slices.
Excellent.
Discovering baby Julia sets.
Yes.
And unraveling the mysteries of those captivating spines.
A great deep dive into the interplay between geometry and dynamics.
A huge thank you to you for being our guide through this.
Oh, it was my pleasure.
Complex and beautiful mathematical landscape.
Happy to be here.
And an even bigger thank you to you, our listener.
Absolutely.
For sharing this paper and sparking our curiosity.
It's been a pleasure.
It's been an absolute pleasure.
It has.
To explore these mathematical wonders with you both.
Yes.
And who knows, maybe you, our listener, will be the one to uncover the next hidden gem.
That would be awesome.
Within this mathematical treasure trove.
Absolutely.
Keep those minds curious and those explorations going.
Right.
Until next time.
See you later.